No sign. I've got to be on.
Oh, right. Okay.
Hi.
Hi, Yi. Yeah, thank you very much. So,
Yeah.
just quick. Headroom, you end up.
And we are live. Good morning, everyone. Thank you so much for joining us today. We are bringing you another edition of a fan favorite, one that was done in 2021, I believe, Kian?
I think so.
With the previous committee 2 years ago from CranSEDS. We'll be bringing you today the Space Day conference with a theme on space sustainability. My name is Sarah. Here is Kian as well. And we'll be your hosts for today. So today we'll be covering a variety of topics. We'll be starting out with 2 students coming in to tell us a bit about their research on some topics on space sustainability and the future of space. And we'll be moving on to...
After that, we'll have a short break. And we'll be talking to Emma Ryan, who's going to speak to us about space-based solar power in her work at Catapult, Satellite Applications Catapult.
Followed on by that, we will be having a short interview with Marco Chachin. Can you tell us a bit more about him?
So Marco is the head of actuator development and end effectors at Airbus UK, and he's going to tell us a little bit about his career so far and his use of robot arms to capture asteroids with the Japanese Space Agency.
I'm really looking forward to that. And then we'll be cutting to lunch for a bit. Once we're done, we'll be returning with an interview with Cranfield alumni and astronaut candidate Catherine Bennell-Pegg. It was a delight to talk to her, and I hope you all will enjoy it as well. We'll be finishing off the day after, we'll have a little break after Catherine, and we'll finish off the day with a panel discussion on air and space, politics and law, with a variety of guests. A few from, we have 3 from Clyde & Co. We have a commercial executive from Rolls-Royce, a French philosopher, and a researcher as well in Sweden who will be joining us. I hope you're all excited, and let's get ready into the program. We'll be starting off now with the sustainable research with our 2 students. We'll be joined here today by our 2 guests. We have joining us here, we have Luca Lyon and Yi Jiangsang. Wave and say hi, you're on camera right now. But yeah, we'll start off with Luca, who's going to be telling us a bit about in-orbit inspection and the work he's been doing so far for his PhD and master's, I believe. Yeah, so it should be quite interesting. So Luca, take the stage.
Okay, thank you, Sarah. If you could please already share the slide, I will follow that. Okay, great. So, well, hello everyone, I'm Luca Leon. Thanks for inviting me here. I'm a PhD student at the University of Padua, and today I'm presenting my research work, so in-orbit inspection. In particular, I put like the subtitle of Introduction to a Bigger Solution. We will see why later. If you could please go to the next slide, I'm gonna just present myself really quickly. So I'm an aerospace engineer. I got my master's degree from the University of Padua in 2021. And there I start working on the space debris, in particular, how to active debris, like active removal using Tether satellite. After that, I joined a PhD program in science, technology, and measurement for space, with a clear idea of working on debris. So in fact, the title of my PhD thesis is Mitigation, Protection, and Remediation for Space Debris for a Sustainable Orbital Environment. Since then, I started working, and I'm currently located at the University of Nottingham, so way closer to you. As a visiting student, I will spend 6 months here. Another cool thing that I started doing during my studies is a student project called ALBA CubeSat, UniPD. The aim is to launch a CubeSat. We were selected for the ESA Flyer satellite project, and I'm going to talk a little bit about it later, because, again, it fits the schedule. So if you could please to the next slide. I'm lucky enough to be the first person to present today, so I'm going to be the first one to show you this graph. What is represent? It represents the number of objects currently in orbit. It's still not up to date. It's from 2022, but we can see that as for now, we have more than 30,000 objects orbiting space, and that's a big issue, because as you know, space debris can represent a real problem with our satellite. So if we go to the next slide, please. On the left side of the slide, we have a graph showing the debris population in respect to the intact object. We can see like the green line represents debris, and we can see a huge peak around the 800 to 900 kilometer. And why that? Because like we are way too high in the atmosphere to let the atmospheric drag, the residual atmospheric drag take care of our debris, but still is in a very populated area and of very interest for our mission. So what we can do? Well, as the title of my PhD says, we have three options: mitigation, protection, and remediation. What are those? Mitigation means design your satellite to apply with the current law, so the 25 years after death removal, or probably the newer 5 years. So to let your satellite not become a debris, but deorbit or move to a cemetery orbit. Then we have protection. So what we can do to track and map the debris to avoid collision with our satellite. As you may know, the ISS continually perform maneuver to avoid collision towards debris. And finally, remediation. Remediation means literally take away the debris from space. So to do something actively to solve the situation. And that's where my research focuses upon. Next slide. Part of the remediation is the in-orbit servicing approach. In-orbit servicing means literally going there in situ with another satellite, with an active satellite, and do something on another satellite. Active debris removal is part of in-orbit servicing and means literally to capture and move away the debris. But again, active debris removal is a huge topic, and so I focus on a little teeny tiny part, that's the inspection. So, next slide, please. When we want to capture a satellite, a debris, or anything, we need to know how it is. So normally, we know approximately the orbit the debris is in from ground observation. We know approximately the 3D shape of the target because we have the 3D model of the satellite when it was launched at first. But for example, we have no idea of the surface state of our satellite. The one in this picture is the infamous Envisage, a huge satellite, dead nowadays, bigger than a bus. So what we want to know about this, if we want to capture this, we need to know its attitude. We have some data from ground observation using laser ranging techniques, but for example, we have no idea of the current status of the satellite. So next slide, please. I'm focusing on the 3D reconstruction of the model because we know how the satellite was when we first launched, but we have no idea how it is now. For example, it could have been hit by another debris or a micrometeorite. For example, the solar panel could be no more in that position. An example is that Envisat, we know that it starts spinning after its death, and the cause is not very clear. It could be a micrometeorite collision, a debris collision, maybe just outgassing from leftover hydrazine in the tanks, but we have no idea. So how to get the 3D model of our debris? Next slide, please. So this comes the inspection part of the mission. On the right side of the slide, we can see two mission designs that are currently under development. The first one is SPY, or SPY-I, developed by the Italian Space Agency. It's a technology demonstration to prove the GNC capabilities to do inspection on a satellite. In this case, it's like an under control situation because the target is a cooperative satellite that's been launched with the observer. But the other one, Inspector, is a mission under development at the European Space Agency and is just a normal observer, normal satellite that will observe actually a debris, probably Vespa, the same target as the Clear Space One mission that aims to deorbit, to capture and deorbit it. The things that all these missions have in common is they look at your debris, but what would they do with their observation? The things that they want to do is get a 3D model of our target. What you do normally is using a technology called 3D scan. And to do that, you can use different apparatus. The most common is a LiDAR. A LiDAR is simply a time-of-flight camera. So essentially, it measures the time that the light takes to go to the target and comes back. And from that, gets the depth of your image. Multiple acquisition will give you a 3D model of your target. Other technology that are commonly used in space, but not for satellite, is photogrammetry, that is commonly used to map planets, asteroids, and other objects. Photogrammetry works simply using RGB cameras and post-processing the data. Other 3D scanning technologies that are commonly used on ground are, for example, the structure light. So you have a projector that shines a pattern to your target. Then you capture an image, and from the deformation of the target, you can start reconstructing your 3D model. There are other technology, for example, like contact technology, but obviously they cannot apply on satellite. So what I propose to do is, next slide, please. Having a mission designed this way, we will have a main satellite that here is called mothership that will be equipped with, for example, a robotic arm or any other capturing technology, for example, an harpoon or a net. This satellite must be big enough to capture the target, so cannot be like, for example, a CubeSat, so it will be an expensive satellite. To ensure its safety, instead of being itself to perform the inspection part of the mission, we want to use CubeSat. So the mothership will park itself at a safe distance from the target and will deploy some CubeSat, more than once, ideally. And the CubeSat will fly information around the target and capture images of the target. Using multiple CubeSats allows you to have different points of view at the same time of the target, so acquiring more data in less time. The data will then be pre-processed inside the tiny satellite that will then docks back to the mothership, transfer the data, not through wireless communication, but direct communication because the satellites are already docked. And then data can be processed inside the big satellite that hopefully will have a much more strong computational power. What are the advantages of this thing? First of all, you have small satellites that are cheap, that can move. You will have formation around your target. You don't have to perform a lot of maneuver to cover a full 360 view of your satellite, of your target. And then the data can be processed on board of your satellite, so you don't rely on ground station availability and on ground station post-processing. In the next slide, we can see how I propose to do it on the CubeSat itself. We have seen that LiDAR is one of the biggest technology used right now, but has many drawbacks. For example, LiDAR, as for now, are big in terms of volume, are power hungry, and are expensive, and their mass is very considerable. So they cannot be mounted on CubeSat very easily. There are research in this field right now, so maybe in a few years we will have LiDAR compatible with CubeSat standard, but for now are not great. So the other technology that I propose to use is photogrammetry, so adapted from the other use to a satellite target. How does photogrammetry work? Essentially, it uses normal RGB cameras data that you put through a series of algorithms. You can take multiple photos. The important part is that they will need to have common characteristics between each photos. These characteristics are then correlated. This is called feature matching. And from a series of photos, like a 360 view of your target, you can then reconstruct the 3D model through normal RGB cameras. This can be easily mounted on CubeSat because RGB cameras are pretty available, cheap, light. The processing is not too computational heavy, so it can be performed directly in situ and on your satellite. And of course, for example, since this mission wants to perform a docking maneuver by the end, a camera can then be reused during the docking phase and not only during the inspection phase. Of course, we have pros and cons to this technology. One of the many pros is that photogrammetry is really reliable and can be used to inspect big objects from further away, so we'll have like less details, or you can use like really close by and have a much more detailed object. While LiDAR, for example, has a limited distance that you can operate on. Of course, on the contrary, there are still gaps in the technology. Say, for example, shiny objects are not so easy to reconstruct, and we all know that satellites are mostly covered in mylar nowadays. That's very reflective material. But again, I'm working on it. We hopefully get it working by the end of my PhD. So if you could please go to the next slide, I'm just changing topic real quickly and move to the AlbaSat. AlbaSat is the CubeSat that you're designing and student project. And I think it's relevant to this presentation because two of the 4 payload that is equipped with falls exactly in the protection part that I talked before. In fact, next slide, please. We have one that is the impact sensor. An impact sensor is a sensor that wants to map the sub-millimeter debris population in orbit in LEO. Sub-millimeter debris are not commonly taken care of, and there is not a lot of data about it. The reason is that normally a sub-millimeter will not pose a critical issue for your satellite. It will not destroy it, but it can degrade the solar panel of your satellite, and it can cause problem with your optics if you have like a fine pointing. So we aim to provide a better view of this topic. And the other, we call this payload, other people can call this feature, is having on board of your satellite some corner cube retroreflector that are just tiny mirrors that can reflect a laser shine from Earth. The reflection of this laser can be then measured from Earth, and we can get a proper and super precise orbit determination. With a pattern of this CCR on our satellite, we can also do altitude determination. And why this is important and why this falls under the protection part of this presentation is that this payload is completely passive. So if our satellite, for any reason, is dead or stop communicating, or we have no idea where it is because like the GPS stopped working, we can have a full control of its orbital, a full knowledge of its orbit from ground, so we can track it. For example, this satellite will be fully compliant with 5 years rule end of life. But again, for these 5 years, we can still track it. We can still communicate with other satellites where my now debris is, so they can avoid it. This technology will be implemented on like many Earth observation satellites from ESA, but is not commonly done on CubeSat. So we hope that after our mission and our demonstration will be more common. So if we move to the next slide, I will thank you for the attention. I know this presentation was very brief and very general, but please, if you have any question, feel free to ask.
And we are back. Thank you so much, Luca, for the amazing presentation. It's a really interesting solution, what you're coming up in your research for tackling in-orbit inspection. It's a topic that's very much needed, especially when we're going into a lot of this in-orbit servicing missions. You kind of need to know the status of the satellites before you really go into it. In your design, you are able to see a lot of the attitude, the outside, any outside damage to it. Have you considered any ways, perhaps, of looking at internal damages as well? Because I know a lot of satellites, sometimes the thermal control might mess up or some short-circuiting might happen. Was that something you might have considered in your research?
Sarah, but I lost your audio at one point, so
Oh, sorry,
I didn't get the question.
That's okay, sorry. So I'm saying you are able to see a lot of the external damage to the satellite through your concept design, as well as the attitude determination. Have you considered any measures for looking at the internal damages, perhaps, of a satellite, as some satellites sometimes just malfunction internally due to thermal management, short-circuiting, some things like this? Is that something you might have considered already in your research?
That's one thing that I considered at start. Then I'm moving off of it, actually. Looking at the internal part of the satellite is pretty hard as for now. One of the main issues is that, of course, you need proper technology on board of your own observer. So payload design for that. The main issue with CubeSat is that, as you know, you have little power on board and you have little space. For example, the two missions that I presented to you, the SpyEye and E-Inspector, aims to be a 6U CubeSat. But since you need, well, a 2U at least for the all common subsystem, 1 or 2U for the power system in terms of like propulsion system, sorry. So you'll have with not a lot of space for payload. Looking inside of a thing, you will need different technology that are not really common. So for that reason, I moved away from it and towards more like of an external inspection over satellite. Also because like if we're talking about debris, we're not talking about repairing it, but just like moving away. So yeah, thanks for your question, but sadly, at the moment I have not a clear answer for you and how that can be solved.
No worries.
Yeah, thanks, Luca, for your talk. It was really interesting. So I guess like from the very start of it, I was thinking about like the scale of the whole problem. Like you showed off the graph showing just the number of objects in orbit. And I guess we've all seen movies like Gravity where like the debris problem becomes really, really bad and we need to try and fix it like straight away. So I guess like this technology to catalog debris and try to remove it is still like in its very early stages. How long do you think it'll take until we really become capable of like kind of treating space debris before it becomes too much of a problem, until we can like remove significant amounts of it from orbit?
That's a really nice question, and the answer is not so simple. Well, there's actually the next mission plan from ESA is Clear Space 1 that aims for the first time to prove to the orbital debris, so to capture Vespa is a lambda doctor from Vega. It will be launched in next few years, as every ESA mission is not like very clear when it will be launched. This is not a common thing. The thing that we are doing right now, and hopefully that we can do, is avoid creating new debris. So provided every satellite that will launch will deorbit in time and will not stay there. Sadly, it's not so easy, and it's not very easy to perform an active removal mission. When we talk about smaller satellite, it can be easier. You don't need a big satellite to do it. But for example, there are many rocket booster left in orbit from like the 60, 70 mission. 70 is of course not 60. So yeah, we're talking years, if not decades, towards more detailed things about that. Sadly, it's not a fast thing. We're moving towards it. The research community is moving towards it. But again, not a fast process and not very common. Also because it's not really economical, convenient. So private industry will not move towards that way very fast.
Can you touch up a bit more? Can you touch up a bit more, Luca, on that economic side of it? So a lot of the inspection and servicing is something we really want to do more in this future of space. Do you have a rough estimate already of how much this swarm mission, for example, for you might end up costing if you made some cost budgets for it?
The cost really depends actually on the main satellite itself. Like the thing is that, well, first of all, in my design, we have a mothership. So it really depends on the cost of that. The CubeSat cost is very low. We're talking about a few hundreds of $1,000s, so really reasonable for a satellite. The main body, the mothership, is the big guy here. It really depends on that. It really depends on the technology that you employ. I don't have a rough estimate for that. But again, really depends, and also depends on the target. A good part of the cost for a mission is the launch itself. So if we stay in lower orbit, it'll be a bit easier because maybe we can go as like a piggyback with another satellite. But if you go higher in orbit and you want a precise target, you need to have like an individual launch that will cost you a lot. The issue, the economic part of this thing, is that you don't have any return as for now. So normally, if you have a private investor and you want to launch satellite to do like now telecommunication, you can sell your data to other people and make money out of it. If I want us to grab one debris and take it down from satellite from space, nobody will pay me for that. So it's like a thing that I will do that probably space agency will pay for. But as for now, individual and industrial community will not make money out of it, so they will not invest on it.
Thank you so much for that response. And for those at home wondering and are not too familiar with space is expensive. It's very expensive. When we're talking about a few 100,000, that is actually quite cheap for a lot of space-graded materials. So don't be too surprised. Some missions cost upwards of millions and billions of dollars. Just one last question before we move on. Where'd you see your research going after this? Where'd you see yourself going?
Good question. A question that no PhD wants to answer, actually. The answer is I don't know. I have other research involved right now. For example, I'm working on developing a docking system for CubeSat that actually fit my mission. So it really depends. If that goes on, I will gladly stay in academic career to pursue that. But again, I'm most interested in moving towards industry and research. So yeah, difficult question to answer. I have no clear idea. I have 1.5 years left. I will clear my mind hopefully by the end of it.
That's okay. You still got time then. Well, thank you so much, Luca, for that amazing presentation and for letting us know more about your research on in-orbit inspection. We wish you all the best with the rest of your PhD, 1.5 years. I'm sure you'll do great. And then maybe we'll see Dr. Luca Lyon joining us in a few years' time again. Who knows?
Who knows?
Thank you so much,
again.
Luca.
Thank you.
So next up, we'll be joined by Yijang, a fellow colleague of ours this year, who will be sharing a bit about his work on the in-orbit assembly project that was designed by fellow students this year. Screen is all yours, Yijang. You can start.
Can you hear me?
Yeah.
Yep, all good.
Hi. So, all right. So let's begin. My name is Ichan, and a little bit of introduction. So I am a MSc student. I'm doing like double masters from University of Catalonia and Cranfield University in aerospace engineering. And yeah, I'm happy to present Mario, which is like the group design project that we are developed in our masters and with all our colleagues. So that's it. This is Mario, the multi-arm robots for in-orbit operations. So next slide, please. Since it is a group design project, we have a team of 12 members, and these are the subsystems of our team. So we got kind of the mechanical team, the payload, the missions, and the systems, which is represented by Sarah and I myself. Next slide, please. So, okay, let's tackle the problem. So what are we doing? In this project, we are tackling basically the need for building large structures in space. So there's like a lot of tendency of developing new technologies and new complex structures in space. For example, the James Webb Telescope. It is kind of a really ambitious project, and it is huge, and it is really complex. So in order to build that, the engineers had to do reverse engineering and try to make it fall because of all the stresses that they had to support a launch withstand. So that's really a challenge that it is now a reality, and we are tackling that challenge. So what we want to do is basically provide a solution to build structures and assemble them on space and launch the materials from Earth. That way we can basically repair existing structures and do other stuff. So next slide, please. So what do we want to do? The mission statement that in our project, we want to design and demonstrate the necessary technology for in situ in-orbit assembly of large planar structures. And we're doing that through robotic assemblers to support the next generation of space missions. We have two objectives. One is to demonstrate planar standardized and robotic elements for in-orbit assembly, and the other is to develop like sustainable reference source for space development. So that's one of the main objectives in our mission. So next slide, please. Let's talk about what are the main baseline components in our project. So we have an assembler, which is the robotic manipulator. This robotic manipulator is a 6 degrees of freedom and is capable of carrying around 50 kilograms of mass. Then we have the tile, and the tile is basically the structural element that will host the payload, and the payload can be whatever, solar panels, can be a mirror. It is basically where the payload it will be placed. Then, next slide, please. We're gonna have two vehicles. One, it's called the supply vehicle. The supply vehicle is basically the storage for the tiles. So it will carry all the 112 tiles that we have studied, and we come and we'll basically transport all the tiles. Then we have the hub. The hub will basically host the robotic manipulators. So the robots that will carry the tiles from the supply vehicle and place it onto the structure. So how all these connect, how they look like. So next slide, please. These are the baseline components. And next slide, please. And basically, once they are all connected, the final configuration looks like this. We have the supply vehicle, we have the hub in the middle, and we have the tile and the robotic manipulators on top of it. And the velocity vector will show you how this moves in orbit. So the robotic manipulators will go from the hub to the supply vehicle, will carry the tile that is stored there, and will place it onto the front of the hub. So that way we can construct like a planar structure. So next slide, please. And the final configuration is like this. So the 112 tiles will look like this, and we got also solar panels, as you can show, in the supply vehicle and the hub. Next slide, please. Let me introduce you now a little bit of the mission concept of operations. So we divided the mission concept operations into 4 phases. The first phase will have we will launch the hub, and we're gonna use the Falcon 9 rocket. This hub will carry the 2 assemblers inside, and then once in orbit, we're gonna launch the supply vehicle, which will carry the 112 tiles inside of it. Then we'll enter the second phase, which is the demonstration phase. This phase will last around 2 years, and we'll try to demonstrate all the technologies before putting all the payloads and everything. So in here, we're gonna demonstrate the structural integrity, we're gonna demonstrate the path planning, the rail systems, and all the other challenges that are now currently facing. So the locomotion, transport, AOCS, path planning, etc. And we'll try to collect a lot of data in this phase, and then we're going to move on to the phase 3, which is the operational phase. In this phase, basically, it's where we're going to let the customers place their payload into our structure, and we'll do the operational task. This operational phase will last around 8 years, which is basically the end of life of our reaction wheel and on the structure. And then once everything is done, once everything hits the end of life, we're gonna send all this into a graveyard orbit. Since we're going to launch into a sun synchronous orbit, we're gonna basically separate the hub and the supply vehicle, and then to minimize the risk of collisions. So then if they are in the graveyard orbit in the future, where we can reuse and repurpose all these materials of our vehicle for another purposes. So that's why we're tackling the sustainability issue in our project. Let me show you next slide, please. A little bit of the interiors of our vehicle. So you can see here, this is the little bit of inside view of our hub and the supply vehicle, where you can see the tiles stored in a radial form. That way we will maximize and optimize the space available for the tiles. So next slide, please. And also, we want to tackle a little bit of the path planning, because we're trying to minimize the energy and the power required for the robots to place the tiles. So if you click on it, I think we'll show an image like the animation. As you can see, these are the animation that our robots will follow the path to build our 112 tile structure. And the way it has been built, it's basically using the optimal trajectory for minimizing the power required to build it. So every single point is a node of a tile. So next slide, please. we also want to show how we dealt with carrying and the tiles from the supply vehicle onto the our robotic arm manipulation, and we did that using a MATLAB, and we coded and basically performed a simulation scenario where we used a 5-degree polynomial to simulate how the robots will carry the tiles. So if you click, you can see the animation ongoing, and it will show how our 6-degree of freedom robot will try to carry the tile from the supply vehicle, and will basically carry it around to this hub, and then place it onto the front of the hub, which is where our structure will be built. Again, you can pass on to the next slide. You can, in the next slide, in this slide, if you click, you will see how once the robot reaches the hub, it will try to place this tile with all the payload on the bottom in the front of the door of our hub vehicle. Again, it is non-colliding smooth trajectory and verified and using our simulation. So moving on to the next slide, also we tackled the communication issue. So this is the architecture topology and network. It is quite complex since we're gonna have a really huge data of communication flowing. We have both the communication for the payload and also for the robots and the supply vehicle and everything. So we're going to have a relay satellite which will serve as a purpose for both the supply vehicle and hub to communicate with Earth. We have ground stations, and we are going to have a control center to monitor everything that everything is correct. And both between assemblers and everything, they will be in constant communication to basically know where each other are and perform the assembly without any collision issues. So moving on to the next slide, I'm happy to present a video that we made on our project. So if you click, you can see the video. So this is like the final configuration. We've studied different final configurations, one vertical and one horizontal. And that's a little bit of overview of our project. So moving on to the next slide, we're gonna give you a little bit of overview of everything, and we have learned a lot from it. We first wanted to launch 7 launches, but it was really expensive. And then we set it up that we are gonna use only 2 launches, one for the hub, which is like the central place where everything is controlled, the AOCS and everything, and one for the materials vehicle, which we will carry. And we tackle a lot of challenges, either using one robot or multiple robots. Yeah, that we use specialized robots. Also the locomotion method that our robotic manipulators are using, which is basically using rail systems. We also tackle the transport, storage, and electrical power supply, and the path planning. So we did quite a lot of stuff, and we achieved a lot of them, and identify what were the risks and the drivers. So moving on to the next slide, this is like a little bit of the system architecture view of everything. Again, it is kind of a short presentation. So if you are curious, you can here see all the technical parameters of our mission. And finally, moving on to the next slide, the conclusions of our project. So this project will propose using robotic assembly through Rails and multipurpose tiles for innovative assembly. And we also provide standardized tiles that they will provide locomotion for the assembler, structural integrity, and also build a platform for the payloads. And in the end, as we said before, it is repurposable and modular, so it will allow for sustainable space mission. And it will serve as a reference point for innovative assembly of large structures in the future. And finally, moving on to the next slide, we're happy to present our kind of poster that we presented our colleagues Sarah and Maria in ICRA conference, and I think 2 weeks ago. So this is like also a little bit of overview. And yeah, moving on to the next slide. Thanks for your attention, and feel free to ask any questions if you have. Thank you for all.
Thank you so much, Yijang, for the presentation. Although I was part of the group and we did get to do all of that stuff, I do think it was very valuable showing off the presentation here as well, as it very much comes before a lot of this future expansion that people are wanting to do. You do need to actually build things in space. So can you tell us a bit about what actual applications does this research that we did enable?
So there are like quite a lot of applications. So we didn't focus on an application itself in our project, but we kept it open. Applications that comes to my mind would be space-based solar power, which is like kind of really interesting project, and it's being developed now from both Airbus and ESA, and that's kind of one of the biggest applications that I see. Also, I see other applications like building a really large telescope. I mean, James Webb Telescope is really it is really big, but this will allow for really much larger telescope. And also other applications that come to my mind. We saw that it can also be served as a reference for university research projects. So whatever they want to like kind of rent our tile, they can put their project there, and also communication antennas. But so there's kind of a lot of applications that come to my mind, and that's one of the biggest pros that we in our project.
Thank you, Yijang. And not only this, but it's very much a starting point. So if anyone is wanting to do further research, we are here with this concept. Very much enables a lot of other applications, as you might have mentioned, to be tailored around a lot of the components that we use, a lot of the concepts that we use, a lot of the mission that we used, as a lot of the elements were standardized and very much made for repurposability and sustainability in mind. So
Exactly.
Yeah, actually, on the concept of starting points, this is definitely, well, first of all, I want to say I really love the video. I love Kerbal Space Program, so that was amazing. So well done on that. But on the topic of starting points, like this is kind of what we need to do if we're ever going to branch out into space as a species. We need to learn how to build things in orbit, right? And I guess like a lot of things need to work together like perfectly. Like you showed us the path planning algorithm, the network topology, and it all has to go just right for this structure to be built properly. So when this is implemented in real life, as one of the systems engineers on the project, what do you think the biggest challenge would be in terms of organizing everything?
So what would be the biggest challenge in terms of?
In terms of organizing everything, making sure that everything works together as it should.
Okay, so I think the biggest challenge here would be basically making sure that every component is aware of the other. Like the communication is really important in these kind of projects. So if we're gonna have, since in our project we're using only 2 robots, but if we want to build this in a large scale, we're gonna have to use maybe hundreds of robots operating at the same time. So basically, and they have to be kind of autonomous. It's not completely autonomous, but they have to have, you're gonna have to work without a human intervention, at least like a human controlling them at all time. So that is one of the biggest challenge I can think of. And yeah, it will come. We will still have to research on that, but I think it's kind of doable in the future.
Yeah, but thanks so much for that. Yeah.
Thank you so much for everything and for your presentation, Yijang. We're out of time for questions. If anyone is interested in knowing a bit more, feel free to send us a message and we'll forward it to the relevant authors, both for the Mario project and the in-orbit inspection project. And is it true, Yijang, I heard this project is going to be presented at the International Astronautical Conference as well in Azerbaijan? Is it true?
Yes, we also got selected. So yeah, that we are really proud to be presenting that in, I think, October this year at Azerbaijan. So yeah, hope to see you there.
Well, thank you so much. We wish you two all the best. Next, we'll be heading into a break for shortly 15 minutes, maybe a bit under, where we'll be, after the break, we'll be talking with Emma Ryan from Catapult on space-based solar power. Thank you so much. I hope you enjoyed this first session and see you all pretty soon.
Thank you. And if someone could close the doors as well.
Yeah, we need the doors closed as well, if possible.
I guess we could have done it ourselves, but the posture.
And we are back. Go on, Cian. Your
Yes.
turn.
So, yeah, we're on to our next talk. And this is going to be from Emma Ryan. Emma is a development engineer at Satellite Applications Catapult. And she's going to talk to us about her current work in space-based solar power. So Emma's here now. Emma, whenever you want to start, you can go ahead. You have the screen.
I don't think we can.
So
We can.
We got sound?
You can go ahead, Emma. I don't think we were able to hear you. Sorry.
oh, sorry, could I have my slide pack? That would be great. And then I can get started.
Yep.
Wonderful. So thank you very much for my introductions. That's right. My name's Dr. Emma Ryan, and I'm a development engineer at the Satellite Applications Catapult, and we're based in Harwell, near Oxford. Some of you in the audience may already know me because I helped with a group project at Cranfield University on space-based solar power. So hopefully some of what I'm presenting won't seem new at all. But for those of you that aren't aware of space-based solar power, hopefully this acts as an introduction. So if I could have my next slide, please. So I'll be answering 3 key questions. So why do we need space-based solar power, or SBSP for short? And when do we need it, which is very related to the why. Then I'll go on to explain what it is and how it works. And finally, I'll touch on who is currently working on space-based solar power, including my own career path to get to work on it. And it really is my dream job. It's space and saving the environment, which are my 2 favorite things. So if I could have the next slide, please. So why and when do we need space-based solar power? So next slide, please. I regret putting in all these little kind of content slides now. So rather than me tell you, I'd like you guys to tell me, really. So I believe there's a chat on LinkedIn that you can input into, or otherwise just think it in your head and I'll tell you if you're right or not. So how many Hinkley Point Cs do we need to build to achieve net zero by 2050? And this is global. This isn't just for the UK, this is global. So I'll give you a few seconds to answer that. So it's either A, once a year, B, once a month, or C, once a week. And you can see my love of pub quizzes coming through right now. So apologies about that. So in order to achieve net zero by 2050 globally, we're going to need to build a nuclear power station every week, which is quite a lot. That's massive, considering how much work goes into building them, how many materials are needed, how many people are needed to work on these sorts of things. That is a very, very kind of considerable intervention there. So if I could have, and congrats to those who got that right. So if I could have the next slide, please. So this is going back to climate change and really is giving the answer to why we need space-based solar power away. So what temperature is considered the critical threshold for climate change? Is it 1.5 degrees C, 2.5 degrees C, or 3.5 degrees C? And critical threshold here in this context means at what point will there be irreversible loss or damage to the environment? So I'll give you a few seconds to answer that. And of course, we're already seeing some of the effects of climate change at the moment, really, across the world, with the increase in wildfires and things like that. So the answer is A, it's 1.5 degrees C. It's not a significant amount at all. And so this is across the entire globe on average. It's not just in one area seeing that increase. It is a global average across the Earth. But we are seeing around 1.1 degrees C quite a lot at the moment. So it really is getting closer and closer to that critical threshold. That isn't the critical threshold. It's just kind of the closest one in proximity. And obviously, we'll see other critical thresholds at those other temperatures. It's just going to get worse and worse and worse, really. As Greta Thunberg said, our house is on fire, I believe. And that exactly encapsulates what's going on at the moment. So if I could have the next slide, please. So this sort of summarizes or gives the data behind the questions, really. So as you can see there, we need 2,000 Hinkley Point Cs by 2050, or a considerable amount, over 1 million kilometers squared of solar panels, or 7 million 7 million wind farms. So, or turbines for wind farms, I should say. But the point here is it's not a competition. It's not one power generation method is better than the others. We are going to need all of them to achieve the energy demands by 2050. And as you can see on the in the icons on the right hand side, the current global demand of electricity is about 20 billion megawatt hours a year. In the UK, that's sort of 300 million megawatt hours. So just a percentage of that, but still a significant amount. And just like the global demand of electricity, in the UK, it's also expected to more than double by 2050. And you can see there 50 billion megawatt hours for the globe, and then around 600 megawatt hours for the UK. So that's quite significant. And this is because our lives are more dependent on electricity. We all now need mobile phones for everything, including my rail card is now on my mobile phone. I don't have a physical copy of my rail card anymore. And more of our lives require electricity. It's also, as the world gets more developed, more and more people will need electricity. So at the moment, and with a growing population as well. So at the moment, it's 7 billion people. 2 billion of that have no access to electricity. But by 2050, this is expected to go up to 9 billion, all of whom will need access to electricity. So there's significant things that need to be done. And there are issues with the current, the current ways of generating electricity. We want to move away from fossil fuels and achieve net zero, but we need to do significant work to get the amount of wind turbines, solar panels, or nuclear power stations needed. And obviously all of those come with other challenges too. So we have to start looking elsewhere. So UKAEA and other organisations across the world are looking at nuclear fusion, but there is a lot of work to be done there, and including the just very fundamental physics of nuclear fusion. So it's not just the engineering and the reality of building it, but the actual physics, the fundamental science behind making fusion work. Rolls-Royce been making small modular reactors, and that's nuclear fission. And there's quite a lot of, money and investment going into that, because that's a viable option as well. But I'd like to touch, as is the title of this presentation, on space-based solar power. And space-based solar power is another viable option for achieving net zero by 2050 and reaching those electricity demands as well. So if I could have the next slide, please. So as I said, you've got those different options to pathways. One that I didn't touch upon was also hydrogen. This is being had a lot of interest in the aerospace industry as a replacement for traditional aeroplane fuels. It can also be used in other areas as well, such as maritime. A lot of our life now does depend on maritimes because a lot of globalization is brought over by shipping lanes across the world. We need technologies that are affordable and reliable, as I'm sure we're all suffering from at the minute. Our energy prices going up does have an effect on our day-to-day lives, and we need to make sure that any future ways of generating energy is affordable and also reliable. It needs to be resilient. So this has become more of an issue in recent years with the war in Ukraine and COVID. Well, obviously, resilience is critical, and that's one of the reasons why we've seen an increase in price. There isn't that security of supply that we'd normally expect. We also need it operational at scale by 2050, and I believe the UK also want to legislate net zero by 2030, which is the most ambitious out of all the countries in the world. But certainly because of the Paris Agreement and things like that, it's in law for 2050. But it also needs to have other effects as well. So the energy market is growing and growing and growing, and certainly electrifying things is bringing far more jobs, a whole new industry, and generally prosperity as well. But as I said, there are challenges. So for a lot of the renewable techniques that are being used at the moment, you need storage, because they are not, I'm going to use the word consistent. For example, it's not, although it may feel like it sometimes, it's not windy all the time. So you won't get baseload power. Baseload power here means the amount of power you need to just constantly fulfill demand. So just that constant requirement, really. So for anything like wind turbines, also tidal, anything like that, and solar, particularly in this country, you need storage. And in fact, it's incredibly difficult to store the amount of electricity that's required for a country's demand. You also have to make sure it's sustainable. So there's no point using a renewable technique if, say, the manufacturing techniques lead to more damage to the environment to make the parts required, say, for example, for the wind turbines or anything like that. So it's got to be sustainable. You've got to be able to scale it. So it can't just be viable, one, at a lab setting, but also it's got to be viable across the entire population of the UK and also the entire population of the globe as well. And these things are expensive. So a nuclear power station costs tens of billions of pounds to make. And going back to that previous slide, we need loads of them. So it's a very, very, there's a lot of expense related to these sorts of things, and we need to prevent that, or certainly reduce it. Some of them, space-based solar power included, but also hydrogen and some of the other, like nuclear fusion, they have a low, what we call a technology readiness level. So this is just an indication of its maturity, an indication about how viable it is outside of the lab, really. And a lot of them do have a low TRL, and it is going to cost a lot of money to develop them to the point where they can supply to the national grid. And there's also politics involved. So there always is. So the reason that this has got a lot of interest at the moment is luckily politicians, MPs have got interest of it. But we want to make sure that it's done right and not just done for the sake of getting votes, but they are considering all implications of the different techniques and making sure that they're making the right choice for the earth and not just politically. So next slide, please. So one option to overcome all of those issues is space-based solar power. So I'm now going to go on to describe what it is and how it works. So if I could have the next slide, please. So you guys are actually going to answer some of these questions for me. So what is the ratio of solar energy per unit area in the UK compared to space? Is it 1 to 2, 1 to 5, 1 to 10, or 1 to 20? So that's A, B, C, and D in order. So solar energy to get to Earth, to give kind of some of it away, it's got to come through the atmosphere. And there's lots of other reasons why you may not get the full power of the sun on the Earth's surface. We've got nighttime as well. People always forget about nighttime. And then, of course, we have the lovely British weather. So I'll just give you a few more seconds to either type your answer in LinkedIn or think it in your head. So the answer is about 1 to 10. This is always a point of argument and contention, but judging from what I've Googled recently, it is 1 to 10. And as I say, this is because if we go on to the next slide, I won't give it away just yet, but this goes to show that in space it's about 100 watts a meter squared on average, and in space it's about 1300 watts per meter squared. And that's because solar energy is, as I said, lost through atmospheric absorption, reflection from clouds, kind of water in the atmosphere, nighttime, and various other aspects. And I believe, if I remember my slide pack correctly, we can see this on the next slide. So there you can see it's not the best of diagrams, I'm afraid, so you might have to zoom in a bit there. But what you can see there is all the ways that energy is lost to get down to Earth. So for terrestrial solar, as I say, nighttime, you're losing 50% of it, if we're assuming on average like 12 hours a night. You've got atmospheric, seasonal weather, and then you've got the actual conversion of the electronics. So once the solar power gets to the solar panels, there's some losses there as well. Whereas on the left-hand side, with space-based solar power, you get a lot more of the energy out of it at the end. So you can see about 0.02% to 5% for terrestrial solar, so that's solar panels on Earth, but for space-based solar power, about 30 to 40%. So it can provide a lot more energy than a terrestrial solar farm could. So if I could have the next slide, please. So I went into showing how efficient space-based solar power was, but I'm going to just take a step back to explain how space-based solar power works. So in its most basic form, really, it collects solar energy, it converts that solar energy to power, and then it transmits that power back to Earth. And you can see that in a diagram on the right-hand side. And it achieves this in a number of different ways. So you'll have what's known as photovoltaics. It's certainly one way of converting solar energy. So these are just what we call solar panels traditionally. So it collects the solar energy by using huge reflectors to reflect the sunlight onto the solar panels. It then converts the solar energy to electricity using the photovoltaic effect. And then it transmits that power back to Earth, typically using microwaves, the RF frequency. So there are some concepts using laser. There's a number of reasons why that isn't a good idea, and I'll come on to that. But typically, most of the concepts that are out there for space-based solar power consider using microwaves. So this is not too dissimilar to, comm satellites at the moment that generate microwaves back to Earth currently. So those microwaves are then picked up by a rectenna. So that's a receiving antenna. And then that's committed to a power station. And the power station then sends it to the power grid. So that's what we've got there in that diagram, really. So if I could have the next slide, please. So these are the various benefits of space-based solar power compared to perhaps other techniques, but also just generally why space-based solar power is of interest to achieve net zero by 2050. So you get continuous baseload power. Obviously, there's no weather in space. You don't have to worry about nighttime in a geo-orbit or orbits further out because it's outside the shadow of the Earth. You do have some eclipses at 2 points during the year, but they are about, depending on what orbit you're in, about an hour in geo, for example. So they're not something to be too worried about, unlike on Earth where you have nighttime half the time. And this, because it's continuous and due to other costs associated with the space-based solar power system, it's a competitive cost of electricity. So this is called a levelized cost of electricity. And it's just a measure of all the things you have to pay out for to make it happen versus like how much you then pay for it. So how much power you then get. So you have to pay for obviously the system, getting into space, all things like that. But it's still less than got a lower levelized cost of electricity compared to, say, nuclear. So that's very, very competitive, and it is comparable to energy generation techniques at the minute. You also have security of fuel supply. So as I said, it's up in space and it's quite difficult to attack. It's not dependent necessarily on supplies from other countries or any sort of supply chain. Once it's up there in space, it is there. And it is resilient to hostile threat. So it is a risk that it can get hacked. But as long as you have, like any satellite really, as long as you have resilient cybersecurity and also against any sort of physical security risks, it will be resilient and you don't need to worry about any hostile activity necessarily happening on Earth, as we've seen in recent years. It's scalable and safe. So because of the use of microwaves and the physics behind the process, where you control the power density, so that's the power of the microwaves coming back to Earth, it's safe. It won't harm the environment. It won't harm wildlife. It won't harm people. It's definitely not a death ray. So and I can go on to any questions about that if you'd like. Because of the physics behind it and the nature of how the microwaves are being beamed back to Earth, it's at such a low power density that it's not a cause for concern. A bit like Wi-Fi in your house and that sort of thing. Like you're not worried about walking across, I'd say Wi-Fi beam, you know what I mean? Like the Wi-Fi waves. So similar sort of here. And it's scalable. So you can make it, you can send up as many satellites as you want really, and that will allow it to scale. It also has a low carbon payback period, particularly compared to other techniques, because there's very little infrastructure required apart from the rectenna site, which is all those receiving antennas back on Earth that receive the microwaves. So I think it's estimated anywhere from 6 months to 6 years in terms of all the carbon used, and that includes development, manufacturing all the parts required, sending it into space. So it really is beneficial for the environment, and it has generally a low environmental footprint. It can also, depending on how fast development programs go, it's possible to get an operational system by 2040, and it integrates with other technologies. So say, for example, if there's waste heat generated by the rectenna site or excess electricity used by the rectenna site, that doesn't have to go to waste, as sometimes happens, say, with wind power, where I can't remember quite what the term is, but they're basically paid to dissipate it and lose it. You can then use it for desalination and other things. So that's quite useful as well. So as you can see there at the bottom, yeah, it can be used to generate green hydrogen and can also be exported. So although you might want the satellite communicating just with your antenna site, which for example could be based in the UK, you could also communicate with other antenna sites in other countries and export to other countries in that manner, or export in a traditional manner as well with electricity. So if I could have the next slide, please. So here you can see again, you might have to zoom in on this diagram, but here you can see all the different functions related to space-based solar power. So at their core level, they can be sort of summarized as collect, so collecting the solar energy, converting it to electricity, transmitting it back to Earth, receiving it on Earth, converting it on Earth from radio waves back to electricity, distributing it and connecting to the grid. And there you can see all the kind of subsystems that are required to make this happen. And this is true across all the different architectures and concepts for space-based solar power, which I will be coming on to. So you'll need structure, you need the actual system. You need thermal management because of a number of different reasons. One, you've got the heat from the sunlight, and you've got to make sure that that doesn't degrade your structure at all, cause expansion that may cause issues. But also when you go into the eclipses, so those sort of very short periods of nighttime in various orbits, you've got to make sure that thermal transients won't cause any issues in the system as well. You need a control system. So that's basically a system to tell everything what to do. So whether that's how much it needs to convert, how much it needs to collect, how to transmit it back to Earth. You need station keeping, so to keep the satellite in the orbit and where you need it, and also communication as well. So you need to communicate back with the ground, which will tell you perhaps how much electricity you need or how much power you need to send back, but also will communicate where in the orbit it is, perhaps any health monitoring. So I'm getting a bit into detail here, but there's various aspects that require communication. And then on the ground, I'm not going to go too much into this because ground stations are relatively well established. Power stations are nothing new, but the only bit that's unusual is the rectennas. So the things that will be receiving the power. And for a space-based solar power system, in order to keep the power density low so that it's safe, the rectenna site does need to be relatively large. So we're talking sort of kilometres in size there, kilometre squares in size. So it's quite a large area, and that is something completely new. And then the interface with the pre-existing energy system, the national grid exists. That's already there. So that's well established as well. There are other enabling systems that we have to consider. So I was chatting to the hosts earlier, and some of them were working on this. So the in-orbit assembly and maintenance. And this is becoming a larger area of interest, not just for space-based solar power, but for a number of different activities happening in space. For example, like space manufacturing and other bits and pieces. Because we are so reliant on satellites in our day-to-day life, it's quite critical that we do maintain them and we are able to assemble them as well. So that's all quite exciting. And then a big one, which I love because I come from a company called Reaction Engines, which I'll come on to talk about, but launch is critical. So that's a massive enabling system. A lot of the architects, the concepts that have been designed for space-based solar power are kilometres in length. So just to give you a sense of scale, the ISS, the International Space Station, is about 100 metres in length. Now, we're talking things that are kilometres in length, anywhere from 10 to about 15 kilometres. This is about 1,000 times larger volume-wise than the ISS, and we want to put that in space. So we're going to need a lot of launches to achieve that. So launch is also critical. Another area that's quite critical that people don't tend to think about because it doesn't seem interesting, but it definitely is regulation. So this is completely new. This has never been done before. Wireless power transmission, there's been odd bits and pieces, but never at the scale that we're considering from space. And we need regulation, policies, legislation to make sure that we can do that safely. We also need to make sure that we can transmit the microwaves back to Earth. So you have a bandwidth allocation. So this is all ComSats have a bandwidth allocated to them, and that's what they can transmit back to Earth using. And we've got to make sure that we can use that for wireless power transmission as well. And it can take up to 12 years to achieve a bandwidth allocation. And an organization called the ITU sorts that out. So there is considerable amount of global effort to make sure that space-based solar power can get the regulations that they need in order to make it work in terms of net zero. 12 years is simply too long. We're not going to achieve a demonstrator in the required timelines if we have to wait 12 years to even know if we're allowed to do it. So things need to happen, I think, a little bit differently for space-based solar power to become a reality. So I'm not going to touch on all of those. I am going to go to the next slide, but hopefully that gives a bit of an indication into how space-based solar power works. So we're now going to go into a little bit of the history of space-based solar power. So when was space-based solar power first suggested? Was it 1923, 1941, 1968, or 1979? And you get bonus points if you can tell me who first suggested it. So for some of you, this may be a complete guess, but I can tell you it's A, 1923. Many people think it was Isaac Asimov that mentioned it in 1941, but it was actually suggested previous to that. So if it's been an idea for a long, long time. If I could ask you to go on to the next slide. I've just got another question before we move on to the history of space-based solar power. Who first demonstrated space-based solar power? Japan, the USA, the UK, or China? So it's B, the USA, and there will be a video of that demonstration from 1979, I believe, possibly 1975. But all of these countries are also working on space-based solar power, and Japan has done a number of different demonstrations and are the world leaders in wireless power transmission. So if I could ask you to go on to the next slide. So just a very brief history of space-based solar power. You can see a bit of a timeline there. So it was actually Konstantin Tsiolkovsky that first suggested space-based solar power using space mirrors to concentrate sunlight to Earth. So not quite space-based solar power because you're not generating the power in space, but you are making sure that you can get more of the sun's power back to Earth by using mirrors, which is not too dissimilar to what Isaac Asimov mentioned in the short story Reason, which I thoroughly recommend. And that also includes the use of microwaves to beam the power back, which is quite exciting. A gentleman called Dr. Peter Glaser, an American, patented the first space solar power satellite in 1968. And then there's been various studies and demonstrations since then. So if I could ask you to go on to the next slide, and what's bound to happen is this video is not, oh no, it might work. The video going to work? So this is the demonstration of wireless power transmission from 1975. And the video is about similar quality to my webcam. And here what they did is they transmitted power across 1.5 kilometers on Earth. Now, we're talking about geo typically when it comes to space-based solar power. So we're talking about 37,000 kilometers. So a bit of a larger distance, but this was a wonderful first step in that direction. And there you can see the transmitter and the receiver as well. And they managed to get quite high efficiencies too. So that was really, really exciting. If I could have the next slide. And you may have seen that Caltech has done demonstrations recently as well from space, which is really, really exciting. So what I would now like to talk about is why this has never been done before and why it's now feasible. So what is the cost per kilogram of the space shuttle? So that's, from a while ago, compared to the Falcon Heavy. So that's SpaceX. Is it 8 to 1, 18 to 1, 28 to 1, or 38 to 1? Just because I am running quite tight on time, I'm just going to briefly tell you the answer, which is 28 to 1. So if we could go on to the next slide, which has just some facts about how we've come down massively in cost from $65,000 a kilogram now down to 2.3. So that's now why space-based solar power is feasible. When NASA did their studies a while back in sort of the 1970s, they determined it wasn't feasible simply because of the high cost of launch made it non-economically viable. But now with people like SpaceX and Blue Origin massively, by orders of magnitude, bringing down the cost of launch, it's now feasible to launch these 2-kilometer structures up into space in modular form. It's being assembled in space. We're not launching the whole 2 kilometers in one go, but certainly doing it bit by bit is still going to be expensive. So that's why it's now feasible. The physics is all there. Wireless power transmission has been demonstrated, not the full distance, but certainly, some initial demonstrations there. And now that costs of launch are down, it makes it economically viable and we can go ahead and proceed. So if I could have the next slide, please. So this is just kind of iterating what I previously said. So here you can see kind of cost per kilogram and how it's come down over the years. And they think Starship will be even lower. So that little dot in the far right will come down just an incredible amount. And we're looking forward to it when it does achieve that. Also, the cost of developing spacecraft has come down massively. The materials involved in satellites are much lower mass. And there's also been considerable development of technologies like space robotics and the efficiencies of photovoltaics, of solar panels as well. So all of these have resulted in a perfect storm to enable space-based solar power. So if I could have the next slide, please. So here are just some examples of different architectures of space-based solar power. So you've got Peter Glazer's original design up there, but there are various different kind of taxonomies. So there are ones that use concentrators. So that concentrates the sunlight, which means instead of getting just sort of that basic one sun, you can get 100, 1 to hundreds of suns. But also there are aspects that use non-concentrator. So you just get the sunlight directly on the solar panels and they deal with it that way, but they tend to have not as efficient like power density and that sort of thing. The other key difference between the two, between different designs, is having moving parts and not. So with space-based solar power, you always have to be pointing at the sun to get the sunlight onto your system. And you also have to be always pointing at the Earth to transmit the power back to Earth. So in order to always have them pointing both ways, you can either have rotary joints to make sure that you move your satellite so the mirrors or the reflectors are always pointing at the sun, or you have to move it so the bit facing the Earth is always pointing at the Earth, because obviously they're orbiting around each other. Or what you can do is use electronic beam steering, which is a really exciting concept I'd like to briefly touch on if we could go to the next slide. So I'm going to focus on Cassiopeia. This is a UK patented design, and this is a particular design where the reflectors are always pointing at the sun and the structure necessarily isn't, because it's rotating to make sure it's always pointing at the sun, but you get electronic beam steering. And this is achieved by having lots of different antennas that then, due to constructive interference and what's known as a phased array, can point the beam towards where you want on the Earth. So rather than the whole physical structure having to be pointed towards the Earth, you just have the beam, you can direct the beam to where you want it. So you convert the solar power to electricity, and then you use that electricity to either beam radio waves or amplify the radio waves, the microwaves, sorry, in the radio frequency, I do apologize, to amplify the microwaves. But you have all these different antennas that are all have their own signal and they're beaming back towards the Earth, and you make sure that they're in phase in a certain way that it points in the direction you want. So that's how it's achieved with Cassiopeia. I think Caltech are using a similar mechanism, and that's all very, very exciting. So you are facing towards the Earth, but just your beam is using some very, very clever electromagnetic science, which I don't fully understand, I have to admit. So that's what we've got there. If I could move on, if that's okay. So who works on space-based solar power? So hopefully I've got enough time to just briefly discuss this before answering any questions you may have. So if I could have the next slide, please. So as I mentioned, the USA, China, Japan and UK are all working on space-based solar power. Also Europe in general, so the European Space Agency are working on it under the Solaris program. Canada, South Korea. So it is really of global interest at the moment. And I'm going to focus on some of the efforts here in the UK, because that is what I work on. So if I could move to the next slide, if that's okay. So in the UK, but this is a global initiative initially set up in the UK, you have all these different organisations working as part of the Space Energy Initiative. And the Space Energy Initiative is an organisation brought together to try and be the voice of space-based solar power and just represent all the different organisations in there and just make sure there is a focused effort for space-based solar power to make it work. And there is a lot of organisations out there, which is all very, very exciting. And the people that founded, the co-chairs and founded the Space Energy Initiative work at the Satellite Applications Catapult, where I am, and also Fraser-Nash. So I'd just like to move on briefly to what the Space Energy Initiative do. So they've got various different technical working groups who work across those different topics. So communications, that being sort of marketing and driving interest for space-based solar power, making sure that supply chain is engaged and that all the like manufacturing partners and industry partners are there to make space-based solar power happen. There's the technical working group, which I lead, to make sure that we fully understand all the science, all the engineering behind space-based solar power and overcome any issues. And also related to this topic of sustainability, there is also an environmental working group. So a lot of the work they do is on life cycle assessment, which is critical. So understanding all the environmental impacts across the entire life of space-based solar power. And that's not just when it's in operation, which a lot of people do, but it's right from development, right from those initial design stages and people driving their cars to the office and the carbon footprint of that. So I find it a really, really interesting area and an area that does need some work to make sure that all the data that we have is accurate and is valid. So I'm more than happy to answer questions on that later on. And then you can see some of the activities on the right-hand side. And one of the key outcomes of this, of the SEI, is setting up Space Solar, who are an organisation designed to commercialise space-based solar power and really make it happen using the efforts of the SEI. So if I can move on to the next slide. So Space Solar have come up with a 12-year development plan. I think it was originally 16 to 20 years, but we decided to be a bit quicker because who doesn't like feeling stressed? And it's essentially, we're going to de-risk all the risks associated with it and make sure we fully understand all the current unknowns. We're then going to demonstrate space-based solar power. We'll then go on to commercialize it, so to make sure it's economically viable, and then we'll make it a reality. Then we'll realize it, then we'll industrialize it so it can create power for your homes. And down at the bottom there, you can see all the different demonstrators. So the first one will just demonstrate wireless power transmission and the beam steering that I mentioned. We'll then go on to make a 10 megawatt demonstrator in space that will power 1,000 homes. Then we're going for 100,000 homes and eventually kind of a whole town or city. So this is happening across 12 years, and the structure at the end of 12 years is going to be 2 kilometers, which is 1,000 times bigger than the ISS and is considerably bigger than anything we've even made on Earth. So hopefully, I'm talking quite quickly to demonstrate like how quick we have to go to make this happen. So yeah, it's quite exciting, but quite ambitious as well. But it has to be. In order to make a difference by 2050, these are the sort of timescales that we need to reach, because 2050 really is not that far away. If I could go on to the next slide, please. So I'm just going to very briefly touch on some of the areas. I think I've touched on some of these areas that are being worked on by Space Solar, who are an organisation looking at space-based solar power. And if I could just go on to the next slide. And these are, if we go more into the detail of the technical aspects, which some of you may be interested in, these are subsystems that have to be considered, that have to be developed, that have to be manufactured at mass scale in order to achieve space-based solar power for Cassiopeia. For example, CPV, concentrator photovoltaics. These are highly efficient solar panels, multi-junction, to make sure that we are converting as many of the wavelengths of the electromagnetic spectrum as we can, for example. We've also got to work on the reflectors, so the mirrors themselves. These are going to be absolutely enormous. And we need to make sure that we can deploy them in space. We need to make sure that they will survive over 30 years. We need to make sure that they have the appropriate tolerances so they can reflect light onto the photovoltaics, because this 2 kilometer structure, we're also working at a very, very small scale as well. So the concentrated photovoltaics might be sort of 10 mil by 10 mil, but we've got to make sure that those are all okay across a scale of 2 kilometers. So the tolerances on this structure are going to be significant, or we need a way round to account for that. There's also station keeping. So again, trying to keep this structure where it needs to be in orbit, 37,000 kilometers up in geo, perhaps, or other orbits at a 2 kilometer length. So that's going to take considerable amounts of work, and that's never been done before. And also the scale of which we want our phased array and our rectennas. So making sure that the rectennas receiving the microwaves from space are as efficient as possible. So there is considerable amounts of the technical side of things to be done. And all of this, as I say, needs to be done within 12 years, and it needs to be manufactured at a mass scale that's never been done before. I think the number of CPVs we need for the first of a kind, we make as many in a year currently as we will need in a day. So that's the sort of scales that we're at. So yeah, lots of work to be done. If I could go on to the next slide. So these are different organisations that this project is completed, and there is a video on YouTube talking about this, but they've worked on various different aspects of space-based solar power that I've talked about. So like regulations, cybersecurity, the environmental impact study. So I had to write down as a risk, and I never thought I'd do this. There is a risk deer may damage the rectenosite because deer can jump 2 meters. So there are some mad stuff going on. And we also have to consider dolphins and whales because they may also damage things if the rectenosite's offshore. So we have to consider things that have never really been considered before, which is good fun. So if I could go to the next slide. So this got announced the other day. So we've received considerable amounts of money from the government, the Net Zero Innovation Programme, or NZIP for short, working on all these different aspects of space-based solar power. This is also kind of overseen by the UK Space Agency, who we're working with very closely on this, to develop all these different aspects for space-based solar power. So the government will be able to see how important this is and what value it can add, not just to achieve net zero, but these are areas that the UK could increase their industry in. We have a massive semiconductor industry, not quite on Taiwan scale, but in the high-end semiconductors. And that sort of technology can be used in space-based solar power. So it's a huge new industry that could bring a lot of prosperity to the UK in all these areas and beyond. Next slide, please. So just very briefly, I'm not going to talk too much about my career path, but there it is in pictures. So I did physics and then did a doctorate in materials science with Lockheed Martin. I then worked at Reaction Engines on Sabre and also put the technology into other industries. And then there's me on top of a satellite testing thing just out the back there, seeing if we can use it for our demonstrator. So I'm just going to touch very briefly on the next slide. Just the sort of things I get up in my day-to-day. So at the moment, these are the sorts of things I'm doing. So I'm also the technical lead for launch, given my experience at Reaction Engines and my just general love of space. So I've got to come up with a strategy for launch, so how we're going to launch the whole structure up there. And I also, there's a lot of technical aspects of that, such as modelling delta V of different launch vehicles and orbits and having a good understanding of perturbations in different orbits. So I'm really excited to be getting into that. I've also been reviewing materials that we need because they need to be RF transparent, but also strong enough to withstand radiation in space and all that sort of stuff. So I'm getting to do some hardcore material science again and electromagnetism, which I'm really enjoying. And there's other sides, so prototyping being practical. I've been doing studies, reviewing literature, writing bids to get more funding and development requirements, and a whole bit on systems engineering. So my day-to-day is very varied, but I get to be involved in some really interesting things. And it's both technical and programmatic, and I love all of it. So apologies, I didn't get a chance to go into too much detail on that, but I just wanted to give you oversight of what I do and leave like a minute for questions. So next slide, please. So hopefully I've answered all your questions. We need to save the Earth and we need to achieve net zero by 2050. It works by transmitting solar energy in the form of microwave to Earth using an absolutely enormous satellite. And who works on space-based solar power? Well, there are lots of people out there already working on it, but in the future, basically anyone that wants to. So thank you very much for listening, and hopefully it gives some time for questions.
Thanks so much, Emma, for that talk. It's really interesting, like, to see all the different technologies coming together to achieve something that's never really been done before. And when it's such a large structure, it seems really hard to imagine, but it needs to happen, doesn't it? So, kind of thinking about that, the numbers involved here are really, really big, and this is going to involve more launches than we've ever done before, probably even combined. So do you envision that all of this would be done with Earth-based resources, or would we need to use in-situ resources in space? Because, we always hear that the material to make solar panels is really scarce, all of those rare earth metals that we need. So what do you think of that, and what would the costs be?
That is a really, really good question. I think in-orbit manufacturing is going to be very important in the future, but given that this needs to happen in 12 years and due to the maturity of in-orbit manufacturing, I don't think for the first of a kind we'll be using that, but I do think we'll be using it for subsequent systems, so for N of a kind, for ones in the future. I think one thing that's going to be critical is recycling in space. So you're absolutely right. For photovoltaics, a lot of the materials, we're going to need to consider very carefully how to make the system as efficient as possible, so we don't use up too much material and we don't exhaust the planet, say if it's gallium supply. So we need to be doing recycling in space. We are going to have some sort of like warehouse / repair shop in space to be able to reuse those materials or repair anything, so we don't have to create more parts. So yeah, it's a really interesting question, and I definitely think in-orbit manufacturing is going to become critical in the future.
And then that way we make it as green as possible, I guess. Yeah.
Yeah,
thanks,
exactly.
Thanks.
Thank you, Emma. And it was a really great presentation so far. Such an ambitious project, and I can't wait to hear more about it. And it really builds off of some of the talks we had earlier today from the students on in-orbit inspection and in-orbit assembly. We have a few questions in the chat asking if there's any further research that is needed to fully understand the potential climate impacts of space-based solar power, and how do we ensure this technology is developed and used sustainably, especially considering it's a very very large-scale power system in the end.
So those are really, really good questions. So there have been lots of people are worried about the microwaves heating up the atmosphere, and initial studies have shown that's not going to happen. That's not how the kind of physics works in that case. But there are some more modeling is required and more physical demonstrations to fully validate and verify that. In terms of the kind of sustainability and the environmental impact, as I mentioned previously, Andrew Wilson at Strathclyde University has done considerable amounts of work on what we call a life cycle assessment. And I think we just really need to focus in on that and make sure that we are considering all aspects of space-based solar power and making sure all the data that we get is valid. So, for example, one of the aspects of it is measuring how much concrete is needed to build the Rectenna site, for example, and then using various different processes to analyze the carbon footprint of that. But lots of private organizations, lots of industry companies are not willing to share that data because it's IP or it might reflect on them in a bad light. So we need some way of encouraging data sharing in a positive way to make sure that we do fully understand the impact of what we're doing. They've achieved it with ASTM, Additive Manufacturing Centre of Excellence, where by sharing data, you get access to other people's data. And I think we need something like that for life cycle assessment. And that's not just true for space-based solar power. Life cycle assessment is important for any sort of satellite or any system at all, really. It doesn't just have to be space applications. So I think accurate data for those calculations is a great first step to understand sustainability.
Thank you so much.
Are there any other questions from the audience?
Do you have any others yourself? I have one more from the audience as well.
Yep, go ahead.
So just one last question from the audience. I think some people were a bit interested in the security concerns of such an operation. They were asking what kind of security threats technology like space-based solar power may encounter, and how may they be tackled?
Absolutely. Well, because of the spacing of what we're calling the dipole, so these are antennas actually on the satellite. Often when people talk about security risks, they're worried about it being hacked and turned into a weapon. But because of the spacing and the wave that then the electromagnetic waves, the microwaves that then generates, it's not possible to turn it into a weapon in that regard. There are there are various risks associated with cybersecurity, and they are being worked on by a number of different organizations. But the key thing really is making sure, just like any power station, it's considered critical national infrastructure. So if it's considered critical national infrastructure, any attack on it is an act of war. So if somebody attacked a power station on the ground terrestrially in the UK, that would be considered an act of war, and we'd then go to war with that country. And it will be the same, I think, for power stations in space. It doesn't necessarily deal directly with the risk, but it's certainly like an aspect of that management. The other aspect is you might want to hack it and then direct the power towards Earth. But in order to do anything in that regard, you'd need a massive kilometre-wide Rectenna site. So I think someone would notice if people were using a 10 by 7 kilometre area to build Rectennas to then try and take the microwaves or do anything with it. So yes, there are cybersecurity risks, but we are very much looking into it. It's a bit of a nothing answer, I apologise, but it is currently being considered, and there is just intrinsic kind of physics behind it, why it is a risk but won't be catastrophic.
Mhm. Thank you so much for that answer. And it's really great to hear we won't be having any Death Star situations coming up soon.
So
It is
yeah,
our frequently asked question on our website. Like, this is not a Death Star.
yeah, that's good to hear. And I think you've explained the rest of the concept really well. I'm definitely sold on space-based solar power, and I think that's all the questions we have time for. So thanks so much for your talk, Emma. It was really nice to talk to you.
Thank you so much,
Wonderful.
Emily.
I'd
It
just
was
like
really
to
great.
mention, if anyone does have any further questions, please feel free to reach out on LinkedIn and find me, and I'd be more than happy to discuss further.
Great. Thanks very much.
And then
Cheers, thank you.
thank you so much for joining
Thanks.
us.
So now we're
go on,
going to
Jay.
go into a break until 12 p.m. And after the break, we'll have an interview between Marco Chassin of Airbus UK and our own head of communications, Hugo Marmonier. So tune in again in 10 minutes and we'll be back.
And
Thanks.
before we just cut, I know there was a lot of questions in the chat about some politics and laws regarding all these things. We will be having a panel discussion at the end of the day at, what time is it? 2:45, where we'll be bringing a lot of people who are more relevant and may be able to answer these questions a bit better. Thank you so much. We'll see you all in a few more minutes.
Bye. And we're back. So our next speaker is Marco Chassin of Airbus UK. He's the head of actuator development and end effectors. And he talked to our head of communications, Hugo Marmonier, about his previous work with the Japanese Space Agency in robotics and capturing asteroids. So this interview is pre-recorded, so any questions you might have, you can forward them to us and we'll send them to Marco later on. So yeah, we have the video right here.
We have the video.
Good afternoon, Dr. Chassin. Thank you so much for having us for this Sustainability in Space webinar. We are CranSEDS, and yeah, thank you for having us and having accepted to speak a bit about your career, your what you've done in the space industry, and the different advices that you may have for someone willing to enter the space industry. So, first of all, could you please? Thank you. First of all, could you please introduce yourself quickly, both on the educational aspect and then on your career, please?
Sure. So, like you said, my name is Marco Chassin. I am currently head of traders and end effectors for the central robotics function in Airbus. So I have a team that we oversee several projects around all the major plants in Europe and with projects everywhere around the world, including China and the US and also Canada. As part of my my education, I'm originally from Venezuela, where I got my engineering degree in electronics, and also my master's in control systems. And later on, I moved on to Japan under a scholarship to get a PhD in space robotics. Specifically, the degree itself is in aerospace engineering with a concentration in space robotics and space exploration. And then since I've had many hats for my career, working on things like autonomous driving, industrial robots, robotic medical devices, and now all the way to aerospace here in Airbus.
Well, impressive. And so today you are in Airbus, but during your PhD, you've said that you've worked with JAXA, or the Japanese Space Agency, in space robotics, and we've seen that you've worked on different challenges, such as the simulation of manipulator for the space station, asteroid sampling, and basically how to catch an asteroid in orbit. So what are the different stakes, challenges, and how did you overcome that during your work?
Sure. So yes, during my PhD, I was very related to several projects and missions that were ongoing, even by the time I joined the laboratory. So the laboratory, the Space Robotics Laboratory in Tohoku University, where I joined, had several very strong links with the Japanese Space Agency, and to some extent NASA as well. As you mentioned, I worked on the simulation of the manipulator of the Japanese module for the space station. That's a full physics-based simulation and visualization of the manipulator for the outside experiments in the station as well. One of my main tasks was to work on the next generation asteroid sampling robots, and this is because the lab itself participated in the ground operations for the Hayabusa mission, which is the first mission that brought asteroid samples into Earth back in 2010, and that mission went all the way down to 2003. And then the last part that you just mentioned, it's the on-orbit capture of satellites. So basically, my laboratory and we have a very strong expertise in how to capture satellites that have gone out of commission over the years after servicing, basically using a technique called the non-reaction null space of the manipulator. Basically, when you have a chaser, a satellite that is chasing another satellite, and this satellite has a manipulator, there's a way of moving that manipulator without using fuel to stop the momentum of the satellite that has not doesn't have any fuel or has gone out of commission. And so by using a specific control technique, you can actually capture and damp out those rotations, for example, in order to hold this other satellite in place and service it, whether that means refueling or repairing some areas. All these projects bring up different challenges for engineering in terms of either we're looking for new ways to save fuel in space, which is a resource that you basically cannot recover after you use it, or through specific control techniques that allow you to have a smarter system in order to do these very complicated space operations.
Okay, so it's more of a control challenge. And a question to extend that aspect would be, can we imagine a future where we have multiple satellites evolving in space to deorbit different satellites? And what would be the challenge to deploy a more complex mission like that, or a broader mission beyond the current satellite layers?
So this is your question is actually something that researchers have put themselves to think about over many years. So there's been a lot of research about building complex structures in orbit, and obviously the cool thing about being able to do this sort of work is that because it's space. And you have no outside forces or no disturbances, pretty much what you do on simulation works as the real thing. So it makes it very convenient for people like yourself and or myself to just do a very complex simulation that shows how everything's supposed to work. And when you have this in practice, it actually works that way. We actually demonstrated this technology in '97. The lab demonstrated this technology in '97 when they actually capture another satellite using a chaser satellite. And if you see the recording of this operation 1-to-1 with the simulation, it's just as it was predicted, because there's nothing actually interfering with the operation, the physics of the system as a whole. And so researchers have used this as an opportunity to develop very complex structures, that could be developed in orbit. Obviously, one of the most interesting challenges is that working in orbit also means, as I said before, you're probably working with fuel, and fuel is a perishable component of your aircraft, your spacecraft. Once the satellites run out of fuel, that's it for you. I mean, there's not enough that you can get out of solar panels, for example. So technology to keep your spacecraft energized, whether that means nuclear technology or isotopes, nuclear isotopes to keep the thing running, is one of the key technologies that we developed over the last few years. If you notice, out of the rovers we've sent to Mars over the last 25 years, the first few of them, Sojourner and the MERs, worked on solar panels. However, Curiosity rover and more recently Perseverance now use nuclear isotopes to keep themselves running for many more years to come. So again, there are conventions to avoid using this in orbit, but these are the challenges, these are the constraints that we need to work on as we're developing more complex systems that can make more interesting things in space.
Yeah, seems fascinating that it has some fascinating challenge, and
Absolutely.
your career has been amazing. So bouncing back on your career, what would be the best advice you could give to someone willing to enter the space industry, especially on the robotics aspect, such as possibly myself?
Right.
And go for it.
I think that, so as you said, is a very exciting topic. I still get fascinated by this. Robotics and space have been the two things in my career that I find so much mystery behind it, so much magic happening, around them, that is really quite cool and quite inspiring. Perhaps the one advice beyond studying really hard and all the usual things that a professor would tell you, I think perhaps the one thing that the practicalities of working in this field makes it really hard is the fact that you need to have a lot of patience. You need to be the kind of person that is willing to look beyond the reward of tomorrow for something that's going to be very long term. Working on these really cool space missions usually means many years of commitment. Between 10 or 15 years, sometimes longer. Some of these examples could be, for example, the James Webb Telescope mission started in 1990. That's 33 years ago. So many people, a lot of people have participated in the mission, but many people never actually saw what the mission could be in the end. They never saw the mission being launched into space, let alone the results of the actual observatory results or images. Another mission interesting like that is the New Horizons mission. So launched in, I think it was 2005. It was going to take 7 or 8 years to actually get to Pluto. So you basically get your mission launched, and the mission goes into hibernation until it gets to Pluto. Then you're just sitting on it for many years. Just you won't get to see all the cool aspects of discovering something new for many years. So I think that level of patience, being able to keep going at it, keeping your vision on where you want to go, is super important to engineers that want to be part of this field. I'm for us personal experience, that's not easy to do. Especially on the fact that you could be working on a mission for 10 years and then for bad luck, basically the mission may explode on the launch pad. So those are the frustrations that engineers in this field have to go through. And once that happens, obviously it's a sad day for you, but you just need to keep going at it. So very exciting things, and we're used to seeing very exciting things on TV with the launch of and the successful missions that for example, NASA has launched over the years. But behind that, there's also a lot of failures that have happened as well. So just need to keep your resolve there and make sure that you do things better next time.
Yeah, sure. Thank you so much. A final question out of pure curiosity. You said that you've been a bit frustrated by the patience aspect of the space industry. Did you choose to go to Airbus, which is a slow-paced industry, but with more sped up compared to the space industry, due to that fact, since you now are able to see your project starting, ending, and through its life implemented on the aircraft?
I don't. Well, I think that it's a little yes and no. So I did switch industries a little bit to see more tangible results on the midterm. Maybe not immediately. Coming to Airbus, I think I've been very lucky to be involved in big projects that have allowed me to see things from conception, literally from paper, to full implementation on the other end. So obviously it requires patience too. I tell people in my team all the time that from the moment I joined Airbus and I got involved in one of our biggest projects here, I did not see any robot for at least 3 years. So the first few years were just working on paper, working on PowerPoint, working looking at designs, concepts, and things like that. It wasn't until year 3, almost year 4, that I started to see the hardware actually coming through. So the reward there is the fact that once you see those machines or those robots doing the work, a lot of those decisions that you took have now translated into machines that could potentially improve the future of aerospace or the future aircraft, right? So it's very rewarding in that regard, but it still requires a lot of patience. I think that the corporate world, it's an acquired taste. From experience, I can tell you, probably 15 years ago, I did not have the patience to do this. Today, I think I'm very well adapted to it. I think it's a positive experience regardless. You get to learn from people that have worked in this industry for many years. Some of them 30 and 40 years of service here, and kind of capturing the evolution of the industry has been very exciting to me.
Yeah, I'm seeing that currently, and that's amazing. Dr. Chassin, thank you so much for this interview. and have an amazing day. Thank you for everything on behalf of myself and CranSEDS. That was an amazing talk. Thank you.
Thank you for inviting me. It just and have a great day and anytime.
Thanks.
And we're back. So yeah, I think that was a very realistic insight into what it's actually like to work in the space industry. It might be years before you see the results of your work, which is good to remember, I guess, as we go into our careers. So now we're going to talk a little bit about CranSEDS itself.
So just real quick, adding on to what you said, seeing someone really go from a bunch of these careers and really jumping around and doing the best that he can is very, very inspiring. Like we said earlier, if you have any questions for Marco, please leave them down below in the chat or send them through us directly through our email at cranseds.ac.uk, cranseds@cranfield.ac.uk.
Yes, that's it, yeah.
We will be able to send any questions and we'll be able to forward them directly to Marco. But yeah, coming on to a little discussion just now whilst we have some time on CranSEDS. So for those of you who are tuning in and do not know a bit about what we do, CranSEDS is the Students for Exploration and Development of Space Club here at Cranfield. We're one of the larger clubs in the UK, and we even won Branch of the Year for our club this year. But this year we've been able to do so many projects. We do just about everything. Competitions, research projects, a few things, which Kian will tell you a bit about. But everything has not been the best. This year has been definitely a bit rough. I can speak it for myself, and I know a bit of the same for my colleagues as well. Someone who was very dear to us and who actually helped a lot organizing this conference here today passed away. Our Vice President, Tejaswi, she is no longer with us. Our hearts, those go out to the family and friends close to her. And it's such a shame to see her no longer with us. We also will not be flying in Portugal again this year, unlike we have been doing in the past few years. At Euroc this year, we are staying local and national with the rocketry. But not all is lost. I know our teams have been putting in so much work and dedication, and we'll be looking at actually launching in the UK. So there is a lot more to come for that, a lot more information, a lot more pictures and videos, which we're very much looking forward to. It will make us really able to make such a flight-worthy rocket this year with all the engineering rigor, everything that you might need and expect, and I'm really looking forward to it. What else are we doing this year?
Well, we're flying even more rockets than just the one that we were planning to take to Euroc. So we also have the National Rocketry Competition, which is currently in its integration and testing phase. So that's also going to be flying in the UK as soon as we have all the different parts assembled and we can make sure that it's did you say airworthy, flight-worthy, something?
Yeah.
As soon as it's flight-worthy, let's say flight-worthy. But actually, CranSEDS is the Cranfield Students for the Exploration and Development of Space. So we don't just fly rockets. We have basically anything else to do with space, we're probably doing it. So we have the satellite design competition coming up as well. That's on the 8th of July, and that's also currently in its integration and testing phase.
You're part of that as well. How's that going?
It's very dear to my heart. As the software lead, those algorithms are really, they're really about to come to fruition, and I can't wait to see them do their intended task. As well as that, we also are developing rovers. So the Olympus rover trial is also coming up. And our team is working really hard on that too. They're also currently putting their rover together, making sure that it does everything as it's supposed to. And as well as that, we're entering 2 new competitions this year. So the first is the in-orbit servicing and manufacturing competition, which is very in keeping with the theme of this conference. So that's all about space sustainability, servicing your satellites without having to deorbit them, basically, being able to visit them in space, making sure that everything is working out properly. And yeah, making sure that they're still functioning.
It's very much a business pitch competition that we're entering for. So we have to develop a product and actually present it to a lot of industry at the end. So I heard great things about that project, and hopefully we'll see it go really well at the end as well. And we have... And
finally, our Race to Space competition, in which we are going to test fire our hybrid rocket engine, which we've been working on for the last couple of years as a long-term research project. So this is this is a type of engine that's very common for students to develop. It's it helps us like learn about the technology going into an engine, the CFD, and yeah, everything that needs to go right for it to fire properly. So that's going to be really exciting to see as well once the technology is all developed for that.
Absolutely, and I heard it won't just stop there as well. There is much more to come. A lot of these projects, we are looking to build upon them from year to year, do much more. So this hybrid engine project a few years from now, we might be able to looking at making something much bigger with much higher thrusts, actually integrating it into
Possibly
our rockets.
into our Euroc rocket.
Into our Euro project, absolutely. Maybe even launching one of these satellites that we're making into space. Who knows? It's all very much still on the horizon. Other projects as well, we might be delving into some more ecology and agriculture projects as well, looking into working with the other departments here at university, the agriculture and water department, and other universities as well. Up north in Scotland, we might be having a little partnership with them, actually working on these projects, as well as on a UAV project as well. So a lot of great things coming up. We'll be very happy to keep you updated on it. So make sure you follow us here on LinkedIn and on Instagram, where we share a lot of these things. And we've done so much more, right?
Well, remember the sky. Remember the sky is not the limit. I think that's the big thing.
It is the big thing. We've done so much more this year as well. We have a lot of outreach events. We did 2 of our major ones were recently, one in January, one in last week at the KS3 Climate Change Conference Summit. One of them hosted in the University of Bedfordshire, the other one hosted in the University of Hertfordshire, where we ran a stall and a workshop for students ages 11 to 14. The first one was on space debris. They had to devise and design little ideas, creative ideas on how to tackle space debris in space. I know one of them made a giant Henry the Hoover to vacuum up all the space debris. A lot of these drawings, we have kept them, and we'll be happy to share them with you in the future if you're wanting to know what the latest and youngest generation is up to and how their minds might be taking us forward. The second one was on the actual in-orbit servicing and manufacturing side of it, getting them to design new ideas, products, and services for this new upcoming space age.
And I believe we had a genius in CAD
We did.
come up with a fully developed model for how he's going to service those satellites. So
it was actually the group's idea. They were wanting to make Formula One in space, inspired by Mario Kart. And one of the kids, during this small session of about 25 minutes where they had to devise their idea, he actually made a CAD model, kid aged around 11 to 14 years of age, a full CAD model of this rocket car. And it was something we'd never seen before or expected from people
and I thought it was impressive when I was able to build a house in Minecraft when I was 10. But you know, making CAD models definitely gets you more jobs. So yeah, he's going to go pretty far, I think.
It's incredible to see what the younger generation is capable of, and I'm sure they'll be very valuable in the space sector. I was able to talk to a few as well in a talk recently I did for the GDST space upskilling course for programming, where I presented at Amazon headquarters in Shoreditch, where we had this class of students who were working with NASA satellite data and telemetry and had to analyze it and actually make predictions, make comments, make a lot of models from the data. These were students finishing up their GCSEs, going into A-levels, and you could see already a lot of the passion and interest from space. So I can't wait to see what everyone is going to be doing. Our last thing that we've been doing as well this year, 2 things. You can talk a bit.
Yeah, just on outreach, this isn't the only conference we've done this year.
No?
We also hosted the UK CEDS cluster event in November for, I think, was it the Midlands region?
It was the Midlands region.
Yeah. So we had a couple of more speakers there, and more recently we hosted a joint event on women in engineering with Airbus just last month. So we had a panel of speakers from Airbus talking about their experiences in STEM so far, and basically how to keep going.
How to keep going, a bit of their advice on their career as women in this area. It was really inspiring. We got to hear from a couple of guests. We had some Cranfield alumni as well, telling about their experience coming through university and then branching out into Airbus, both commercial and defense and space. We had some other contacts as well. We had Vanessa, the innovation manager, I believe, for Airbus Commercial, telling us about a bit about her life story so far, how she came into her role. It was super, super interesting. And we actually had a guest, Georgina, who no longer works at Airbus, is actually managing the, what was it?
She was managing.
She's managing the big association that runs football in the UK and other countries.
Was it UK? No, it was. It
wasn't just UK. But yeah, she
Yeah.
actually is good friends with our next guest will be presenting after the lunch break. Catherine Bennell-Pegg, the astronaut candidate. We'll tell you much more about her soon enough. We also did a well-being campaign as well. We are partnering up with some of the clubs and other people here at university. If you're a fellow member in one of these sports clubs, feel free to reach out to us as well. We did an event with the badminton club recently where we were really trying to promote physical well-being and really getting a bit active, because a lot of these people in engineering, all is fun, all is great, sitting at your desk, sitting at your computer, researching into new technologies for space sustainability, but you do have to be active as well and live a healthy life.
Eventually, you have to take a break at some point if you get the time.
So I hope you've enjoyed a bit of this recap of this year, bit of highs and lows. I can't wait to see what a lot of these new projects will delve into and how a lot of our current competition projects will be able to really become such a great thing. So we have a few competitions coming up in the next few weeks. Can't wait to see how the teams perform and the engineering works that they're able to perform. We'll be able to post all of these news and much more on our LinkedIn and Instagram once more. Make sure you are up to date.
Especially on satellite design. That's the most important one.
Maybe not the most important one, but quite an interesting project that we'll be doing. We'll be cutting to lunchtime right now. We're ending a bit earlier as interview was a bit shorter. Make sure you join us at, what was it?
It's 13:45, so that's about 80 minutes from now.
Yeah, at 1:45, where we'll be showcasing the interview I recorded a few weeks ago with the astronaut candidate, Catherine Bennell-Pegg. Thank you so much for tuning in. We hope to see you all after the break. Have a good lunch break.
See you.
And we are back. Thank you, everyone, for those of you who are still here, or those of you who might have joined only now. We are back on the Space Day Space Sustainability Conference of CranSEDS that we're doing today. Hope you all had a nice break. We'll be resuming the conference now with an interview by an not an ex-student, an alumni from Cranfield. She's been everywhere. Most space agencies. She's worked at quite a few companies already so far. We'll be introducing to you an interview pre-recorded with Catherine Bennell-Pegg. If you have any questions, feel free to drop them in the chat or send them directly to us. We'll be able to forward them to Catherine directly once we're done. So I hope you enjoy. Here's Catherine's interview. Wait.
We should also mention, Catherine, I have to say specifically, is a graduate of the MSc Astronautics and Space Engineering course.
She did a course in 2009, 2010, both her and her husband as well. So let's cut to the interview. Cool. So today we are here with the class of 2009 and 2010. You've jumped around quite a bit in life as well, been a part of just about all major space agencies, and now you're here getting ready to become an astronaut. So let's talk a bit about you, Catherine. So can you briefly tell us how you got here to this point? So a bit about your educational background and what it led you to ultimately pursue, I guess, a career in astronautics and space engineering, which is the course that you ended up doing here at Cranfield, but it matches so well as well your career paths as well.
Thanks so much, Sarah, and thank you for having me. It's a pleasure to be here to talk to you and to address all of you in the audience. Cranfield was such a special time in my life, and yeah, it's a pleasure to be invited to chat with you. I'm sorry I can't be there in person. The training schedule is quite intense, but I'm very pleased we're able to do this record and to have a chat. So my background and how I came to do space. Well, how long have we got? Basically, I've always loved space. I've always loved space. So I'm one of those kids that really never let go of the dream to work in space. And, you know, if the luck would ever have it, to be an astronaut. So I fell in love with space as a kid. I think as a young child, like many kids, I was drawn to the sense of adventure that space is. I was curious about the world around me. I loved looking at the stars. And when I knew that, you know, there were planets and galaxies, not just pinpricks of light, I really wanted to explore those worlds because I was very young when I had that desire. And as I grew up, I was really interested in science, and I love making things and being creative. And at our school careers fair, we were asked, you know, what do you want to be when you grow up? Write down 3 options. And, you know, I only wrote astronaut because I was stubborn, you know, a stubborn 13 or 14-year-old. And that's what really excited me. And, you know, rather than being sent off to find a more realistic career, I was set off on the path to figure out what that would really mean. And I learned that you can become an astronaut through almost any STEM fields. You can be a scientist in almost any discipline, an engineer in almost any discipline, a doctor, a medical doctor, a pilot. And so all of those things appealed to me. So I tried things out as much as you can as a student, and ultimately decided to study engineering and physics for my undergraduate degrees in Australia at the University of Sydney. And to be honest, I found the first couple of years pretty tough. It's quite a slog, but persevered through, and that was absolutely worth it because engineering and physics were so exciting to be able to actually implement, to be able to create new value and new solutions to the world's problems using those tools is very exciting. So in my later years, I really started to enjoy the subjects when you got to do new things, not just check the answers in the back of a textbook. And when I was there in my undergrad courses, there were a lot of exchange students, and they taught me what's possible in Europe for a space career. And I never really had considered anything except NASA before, but I have a British passport through my mother. And so I was able to get involved in the European Space Agency student activities, like some conferences and Rexus Baxus later. And I went over there, first of all, for a space station design workshop activities and the space camp in Norway, European Space Camp. And there I learned about the courses you can do in Europe. And one of them was a course called Space Master, which is, I think you still have the students on the Cranfield University's course. And so I applied to that and was lucky enough to get in. And I basically had a fabulous time living across multiple countries, learning all about engineering. I did internships at NASA and at ESA. And I chose to do my degree for the second year of that course at Cranfield, which is great because Cranfield, I felt the topics really matched my interests in engineering, the mechanical, the propulsion, the thermal, and the systems engineering view, which is something that can be quite hard to study at the undergraduate and postgraduate level in space around the world. And yeah, it was great. So Cranfield gave me the space to complete the Rexus Spexus project, to do my thesis at the European Space Agency in Nordwijk in thermal engineering, and taught me really strong fundamental systems engineering skills and quite advanced systems engineering skills too, that I still use today in my job. I think one of the great things about the course was that it taught me about like the industrial view, the ecosystem view of the space sector, and that helped me to understand that world we live in for space, how it's international, how it's multicultural, how systems engineering is so critical and the role it plays. And even things like the subjects we did, like the thermal software and the mechanical software, for example, helped me to get my thesis internship at ESA, and I used it there straight away. So yeah, very formative experience. I lived at Fedden House, would often be at the student bar, meeting all the other students from the UK and across the world, many of who are still great friends today.
Thank you so much for that. That was quite an inspiring answer as well, seeing you come from a place of such passion as well, and then really going just about everywhere, pursuing the Space Masters. We actually have a couple of students this year doing the Space Masters with us as well.
Awesome.
And it's really great to hear, especially with the systems engineering, because I know that's something Cranfield does weigh quite a bit on, and it's something they do really try to teach you to benefit you in the space industry. So let's talk a bit more about Cranfield and your experience here. So do you think that your experience here at Cranfield kind of influenced a bit your career trajectory, and do you think it contributed to your success all in all?
Absolutely. So at Cranfield, I did my thesis with Jenny Kingston. Hi, Jenny, which is great in thermal engineering. And I went to ESA for that in the Netherlands. And that was great. And Cranfield prepared me really well to deliver on my thesis and at that internship. So my thesis was looking at like the thermal behavior and analysis of two LiDAR instruments on two ESA missions, Aeolus and EarthCare. And yeah, that was the first time I really got to work on a real space mission, and that was really empowering. And my time at Cranfield, yeah, even from the lecturers that taught us about the history of space in the UK and the projects that they'd specifically worked on, set a really great foundation. The industrial connections helped me to understand the landscape in the UK. So we often had people like reviewing us from Airbus or SSTL and other places like that. And yeah, that helped us to build the industry connections. I did my graduate program straight out of uni at Airbus in Stevenage, and a number of people that worked there are people that I already met during my Cranfield degree. So the network was really helpful as well. And I was part of CranSEDS or UK SEDS in my time at Cranfield University, and still remember going to the conferences. So yeah, it's all really, really a nice way to begin your career, working with a lot of other students that you'll keep in contact with throughout your career as you progress. Then you'll do really interesting things in space if that's what you choose to do. And yeah, great foundation.
Thank you so much. And coming back to that, like a lot of these connections that you make during your time here end up being the new generation of engineers of the future. So it's you can definitely attest for it. Like a lot of your colleagues, you'll find them just about everywhere right now. Your cohort from your year, especially a lot of them at Airbus as well, which you end up doing quite a few years on as well. I think 9 years, according to what I have
Yeah,
here.
that's right. Yeah, so I started on the graduate program in Stevenage, and I started in mission systems engineering, which is early phase studies. In Earth observation was my home team, but I also did some science and exploration missions as well. And so I started off straight away doing a phase 0 mission with myself and one other junior engineer, looking at ocean surface current. So we got to work with oceanographers to try and figure out a mission that would deliver on the science that they would want to know, that could fit in the right envelope for the budget and launcher. And right away, I was using the skills that I learned at university, and that was really exciting. And I did other rotations. I worked on LISA Pathfinder. First of all, as a junior systems analyst or supporting some AIT work, sitting in the clean room, logging every piece of equipment that went onto that satellite because its internal gravity mattered. And then I moved to being a thermal architect, a junior thermal architect, supporting the thermal architect for the test campaign. So this is all late phase. And I got to go to IABG or IABG, a big test house in Munich, for a big on-station thermal test campaign, which is where you run the spacecraft through its mission on fast forward in the hot case and the cold case. And by the end of that, I was dreaming the spacecraft. Like you really got a sense of how it all worked together. And then I did a placement in Airbus Bremen, working on space debris removal mechanisms, mostly a net deployment mechanism in the drop tower. So I got some hands-on practical technology development and prototyping work. And then back to the UK, where I did innovation management and looked after how you assess and predict and strategize around emerging technologies and allocating out some budgets for people to do work there, as well as my own. And then back again to mission systems, because I really love the creativity and teamwork in early phase system engineering, where I worked on a few different topics, like a Mars hopper technology development from Mars and other things like that. And then I transferred to Bremen, also within Airbus. In Bremen, I worked again on space debris removal mechanisms and the ED orbit mission, which went to phase B1 to remove MBSAT. And I led an R&D project together, a joint R&D project with Lockheed Martin on what else we could do with the Orion ESM vehicle. So Europe has the service module and the US, the crew vehicle. And looked at, what else can we do with that vehicle beyond the currently planned missions at that time, concepts for Gateway. Eventually, I worked on a program called Bartolomeo, which is now a balcony, in effect, on the front of Columbus, run as a business from Airbus for payload hosting. So that's just some of the projects I worked on, and I've had such a great time with this breadth of the kind of compelling missions that space can do. So yeah, while I fell in love with space and wanting to be an astronaut for the adventure of it as a kid, I think the more I've been in the field, the more I appreciate it for what it can do for science and unlocking discovery in a way that you can't always do on Earth. It's complementary or it adds on. And also for what it does for society, critically underpinning society. And now here at the Astronaut Center, we're learning a lot more about payloads and what you can do in space, because, in space, astronauts are the eyes and the hands of the scientists on the ground that have spent years, sometimes decades, developing their science and their payloads around what you're flying. So, and I'm blown away by the real world applications of what we can do in space station labs. So yeah, it's a journey, but yeah, I've had a fantastic career so far, right from the internships I did all the way up to now. And this is just the beginning of the next phase for me, I think.
Absolutely, absolutely. And with such a portfolio as well, tackling so many different space projects, even going to trying to tackle NVSAT, which I know is quite a challenge, and that a lot of engineers and scientists are still very much trying to tackle. But that's really great to hear. And then after Airbus, you moved back to Australia and went to the space agency. So that's quite interesting. After all those years at Airbus, you went back home effectively. So can you tell us a bit about your work at the Australian Space Agency? Because it's quite new, the agency, compared to some of the others. I know a lot of the projects you're trying to tackle are quite interesting, and there's a lot of innovation coming forth from the Australian Space Agency. Can you tell us a bit about your time here, and especially when you were the director of the space technology and everything, because that sounds like such a cool title.
Thank you. Yeah, so when I left Australia after my undergrad, I did it not thinking that I'd ever be able to return home, because at the time, Australia didn't have a space agency. We didn't have a large upstream sector developing satellites. And I figured that I wanted to develop space missions. So it was overseas for the rest of my life. And So when the Australian Space Agency was set up in 2018, I was really excited, but figured that it would be later in my career when I'd have the skills to be able to contribute. So when they were recruiting in 2019, I saw the ad on LinkedIn. I was on maternity leave with my second kid, and thought, oh, surely to be like a technical manager in a new space agency, I'd need to be at the end of my career. But you know what? I'll throw my hat in the ring, so they know who I am for the future. And my husband did the same. He was also a CranSEDS student. And yeah, they took us both. But we both applied for the one job, said may the best person win. And yeah, they took us both. And, you know, we were loving our time in Europe and our work. And we both had great jobs. And our house was half demolished. But, you know, we figured, you go back at the beginning, you get to really contribute your expertise in a creative way, in a strategic and a technical way. So sort of now, or you wait another 10 years. So we jumped at it. We went home, and my first role there at the end of 2019 was to look at managing the roadmaps activity, which is basically looking at the capability growth path for Australia technically in space. So I was given 7 different topics, space priority areas, which is super broad, like this Earth observation, communications, PNT, robotics, etc. And I had to look around the country and say, okay, where are we today with capability in space and in relevant adjacent fields? Where should we be in 10 years based on both opportunity and need? And then how do you get there? Right. So pretty quickly, I saw that I couldn't do all this on my own, and was able to, my boss hired a bunch of experts to support in this and to work on each of the roadmaps. And basically, I set the method and guided them through in an integrated way. And it was so interesting because a lot of the capability in Australia is from adjacent fields as well. So we got to go out and scout and say the resources and energy sectors and all of that sort of thing to look at what could be pulled into space. Work with international space agencies to try and find their gaps, because our strategy is around contributing value into gaps for the opportunity piece wherever possible. And then I also, through my engineering background, supported the Moon to Mars Trailblazer mission, which is Australia's largest space mission, the Space Agency's funding, which is a rover to the moon. And I was part of pitching that mission concept internally, and then with NASA, and we're working with NASA to send that to the moon in the late 2020s. So yeah, it's really incredible. It's pinch me stuff. You go from working in an organization where almost any kind of expert is at the end of the phone, to really having to understand that what you know and the limits of what you know, and when to ask questions from those around you, and when to hire in experts to fill gaps. But that systems engineering view is what helps to manage across all of those, that breadth of topics, and understanding how it all stitches together. But then, yeah, about a year or so ago, I got a promotion to the Director of Space Technology. And for that, I was looking after the topic of access to space, which in Australia isn't just rockets and space transportation, although it includes that. It looks at accessing the full value chain of space. So how do we develop an upstream industry in satellite manufacture and what type should we be focusing on? And what role should the Space Agency have, if any, in setting that? The launcher sector. So Australia's got a fantastic potential for spaceports. We've got a number of companies of various levels of maturity establishing spaceports, both for a national sovereign need perspective and also from an opportunity perspective to serve the worldwide ecosystem. And we've got rocket development companies, and we've got operators that are already generating revenue. And so how do you pull that together in an integrated way so that we can have a thriving ecosystem in Australia that also serves global markets? And I have a great team of engineers, many of whom moved home from Europe or other places. One was also a space master to contribute to this. And then, yeah, now I'm here. So I've got someone acting in my role right now. And yeah, I'm here in Europe for the astronaut training for a year. So it's been a thrill.
Such an exciting journey, and as well, like joining the Australian Space Agency almost at its infant stages as well, really being able to be a part of it and its growth, working on such key projects as well, almost like working at a startup almost, with the level of infancy it had and how much it was able to grow. Maybe we'll even see a rover and the moon in the upcoming years with all this moon projects going on. So now let's go back to the main focus. You're to become an astronaut, which is really, really exciting. Congratulations on that. Can you tell us a bit about, so we already know about what motivated you to get to this point, a long life passion since very young to become an astronaut. Can you tell us a bit about the selection process and some of the challenges you might face within?
Sure. So, yeah, I applied for the European Space Agency's recent selection process, along with almost 23,000 other hopefuls, perhaps some of you on the call, which was really exciting to see when they opened up the call in 2008. When they last did that, I was still a student, just starting out the year before CranSEDS, so I wasn't eligible to apply. So this is the first time in my life that I've had the eligibility to apply to be an astronaut. You know, in any career, you might never get the chance to apply, or you might get one or two, right? And there is an element of luck involved in whether or not you meet the criteria of that particular round. It always evolves, everything from your medical profile to your personality profile, neither of which you can really change, and to your educational qualifications. So for me, I watched all the webinars that I could about it. I went and had looked at all the documents that I had to do to deliver, and you had to do a motivation letter and a CV. And I stayed up all night writing my motivation letter, because it's really hard to write a motivation letter for a job that's your dream job and not come across cliched, and hitting all the right points. I spent a long time making my CV relevant in the template they wanted. I flew to Sydney. I live in Adelaide. I lived in Adelaide. I flew to Sydney in order to get the right medical, which was very fortunate because it was around the time COVID was shutting internal borders. So I managed to get the medical certificate I needed, and I applied and I waited. And ESA started inviting people in batches, and I was invited to go over, I think it was September 2020, to do the first test in Hamburg. And I was so excited. I had a couple of friends that got in the week or two before me, and was thrilled for them. And the email seemed to come every Friday. And so I was like checking my email on a Friday, and I saw it, that I got the invite, and they give you 3 weeks to you know, do the practice exams and be in Europe. And it was a time where you couldn't really leave Australia because of COVID. So I had to wrap up work, figure out how to exit and re-enter the country. There were almost no flights coming back. I had to get a special travel agent to help me. And if I got COVID, I would have been stuck in Europe for months, which is not ideal, especially when you have little kids. So it was quite a whirlwind, and the tests are incredible. It was a full day of tests in a room in Hamburg. We all were like carrying coffee there because there was no coffee machine, and bags of jelly beans. And it was a day of computer-based tests of all sorts. And for the first time, I got to meet other applicants, and there were about 20 people a day, and they were just so incredible, from all walks of life and all sorts of careers. And there's no sense of competition between you because there's so many still in the running. And how do you compare your career to a medical doctor or a pilot? You can't. So the pleasure of a lot of the process was meeting these other people. And then the next stage after that was the psychology stage, which was at the European Astronaut Centre. And this is the first stage where they really culled from, I think it was 13 or 1400 down to 300 or 400 people. And, you know, you're at the Astronaut Centre, so it's starting to feel a bit real. And there was usually a couple of astronauts on your day as part of the assessment group, and you had 8 people on your day. And that had, you know, a big panel interview, it had a group interview, it had exercises in pairs, it had interviews with psychologists. And pretty quickly you see that, you know, you have to be authentic. You want to show the best authentic version of yourself, but you have to be yourself. And ultimately they're trying to see, do you have the right personality profile they're looking for? But they don't tell you what that is, right? You can guess, but I mean, today people are really looking for astronauts that can work well in team environments for a long duration, as opposed to the alpha personality. And I think there was some magic in that process, because in the subsequent rounds, everyone got on really well. The personalities just clicked. So there's something there. And then the next stage was medical. So medical, we had things like fitness tests. I had a full week in Toulouse. where they did almost every test you can imagine without a scalpel. That was actually kind of a really nice week, despite all the tests, because you're with a group of about 6 or 7 and you're all in it together, and there's no exams or anything beyond, you know, medical exams. So there was nothing to study for. You could just enjoy each other's company and you know, for the first time really feel, you know, odds are one of us is going to be an astronaut, because there was about 90 or 100 people in that round. Then after that, I didn't think I'd get through the medical, just because, you know, I've had 2 kids, I've had a few niggly tiny issues in the past that I thought could disqualify me, but lo and behold, I got through. And that's the first moment where I was like, okay, that was the big hurdle I had in my head. From here on out, we've got interviews. This could really happen. And, you know, ESA said they might pick, you know, up to 25, and there's less than 50 of us left. Here we go. So I took about a month of work and padded out my CV as much as I possibly could, knowing that ESA would know that, but it's better than nothing. So I leveled up my scuba diving, my flying. I started skydiving. I got a commercial drone license and did volunteering using that with Surf Life Saving Australia, building on my patrolling volunteering, and studied some online courses in human spaceflight operations and so on, and studied like hell, because the stage 5 test was about testing your technical competencies and your behavioral competencies. So I whipped out my old Cranfield notes, the ones that I could find, and I was speed reading them as well, because I figured they could ask me anything that I'd ever learned in engineering. And yeah, the stage 5 test was really interesting. And it was a big panel interview, and they really tried to put you under pressure to see if you could handle that while answering difficult questions or questions in other languages as well, because the international angle is really important. And yeah, then stage 6 came, and stage 6 was the final interview with the ESA Director General in Paris. And that was again a panel interview. And all of these interviews have, you know, astronauts or former astronauts on them. And yeah, you just have to put your best foot forward and hope you've got what it takes, because yeah, you can't change much about yourself, but you can just try and explain yourself as best as you can. So after that interview, I didn't get in. So I wasn't selected. Out of the 25, ESA took 17, 5 careers and reservists, including John, the UK para astronaut. And, you know, they're all such wonderful candidates that, you know, I understood why they might be picked over me. But yeah, in my debrief and subsequently, I was informed that a major factor in that was my limited time and connection to Europe, because it's really important that an astronaut can really inspire their home country, and ultimately Australia is my home. So, and that's something I understood. But and so, you know, I was disappointed, of course, because at that moment in your life, you're waiting for a call that can say you're an astronaut, or you'll just continue on with the status quo. And until that point, I think I'd managed to protect myself from any potential disappointment really well, because you don't really believe you'll get through to the next stage every time. But at that point, you know, I think that everyone is very vulnerable. So when I was told I wasn't in, I was very disappointed for a few weeks. And yeah, then just decided to move on. I really love my current job. I love working at the Australian Space Agency and helping to build space capability and missions in Australia. So I was back at that, and then I got a call into you know, an executive's office, and was told, you know, that ESA in Australia, based on my performance, are agreeing to train me on the basic training, but don't get too excited. There's still a few hoops to jump through, but you'd have to be in Europe in a month. So that it was all such a whirlwind, and I'm so grateful to Australia and to the European Space Agency for training me. It's absolutely fantastic to be here, and I'm excited, you know, not just for me, but this is the first time anyone's trained as an astronaut with the Australian flag on their shoulder representing Australia. So that's huge for what it can do for the space sector in Australia, what opportunities it can unlock for payload developers, scientists and engineers, operators, and potentially, I guess, in adjacent fields for human space exploration, like things like rovers and robotics. So yeah, I'll be doing my best in the training to connect as many organizations as possible, and to really unlock those doors and show that human spaceflight brings value, that it's not just a luxury, but it gives you access to all of the microgravity sciences, and in the future, more planetary science with the moon exploration missions as well. Yeah, and I'm training here with Rose, the new British astronaut, who's awesome. And yeah, John will join us soon as well for some parts of the training. And I look forward to seeing Megan in the future. Hopefully she gets her chance as well. So the UK is very well represented here. And yeah, it's a really exciting phase, I think, for the UK as well, being so represented in this astronaut corps.
Thank you so much. And it does really seem like you went through all the hurdles to get to where you are. And I'm sure, especially repping the Australian flag, that you are probably one of the biggest role models right now for people in Australia who are wanting to pursue a career as well in the space industry. Just be mindful of time. I don't know how much I'm allowed to go on for. I'm happy to end it at 7:15. Or if you
I
have...
can check my calendar.
Yeah,
if you like.
might
Sorry, they'll
be
have to cut this bit out of the recording.
Yeah,
I'll
that's
just
fine.
quickly do this. Hang on, sorry. I'm pretty sure I have a little bit of margin. Let me check. Margin's important for engineers, right?
Yeah. See, we started just slightly a bit late, so.
No, it's fine. It was my fault. 1 moment. Okay, I've got till, I reckon I can go till 8:35 my time, which is another 20 minutes
fine.
if you need
That's
it.
more than fine. It shouldn't need to take that long, but thank you so much. Okay.
No, of course.
Okay, we're back. So thank you so much for that answer. So can you tell us more? Can you tell us a bit more about what you're doing nowadays with your astronaut training? What kind of challenges and tasks you have to do, and what are you most excited about right now with your current role?
Yeah, so I'm here on the basic training. So in an astronaut's career, there are a number of different types of training. It starts with basic training, which is just over a year for the European Space Agency of classes that bring you all up to a level at which you can be called an astronaut, no matter what your career background is, and it prepares you for almost any kind of mission in the future. So around the world, amongst all the International Space Station partner nations, there's a common core curriculum for basic training. So you all have the same standard before you can be selected for a long duration International Space Station mission. But it also sets a scene for other missions that may follow, or after your first mission, potentially having a more senior role in space, such as EVAs or robotics missions, or perhaps commander in a subsequent mission. So it's really important skills that they're setting the scene for. After basic training, astronauts go on to pre-assignment training, where they do more learning to prepare to be selected for a mission, or contribute from the area of their expertise to the European Space Agency. Then there's pre-assignment training for a long duration mission, which is usually around 2 years, preparing specifically for what that mission leads, and then the mission, and then a post-mission period before being back to pre-assignment again. So the basic training, for our class, we have 6 of us, the 5 ESA astronauts, the new career astronauts, and myself. Our boss is Alexander Gerst, who's a great role model for us to learn from, and the other astronauts around as well to provide their insights and mentorship, which is fantastic. For us, it's about a year of training. It's such a breadth of topics. So far, we've done biology with DLR, astrobiology, gravitational biology, radiation biology, and they rapidly ramp up from the fundamentals to being really in depth. And we get to do things in the labs. We got to process some of the Artemis Phantoms that recently flew around the moon, the radiation sensors, for example. We've learned about astronauts' careers. We've done human behavior and performance training, and how to be a good team member and leader, and looking after yourself on Earth and in space. We've done presentation training, media training. We've done nutrition this week. We're doing fitness. We need to do a minimum 6 hours in the gym a week, mostly instructed. We started doing scuba training in the neutral buoyancy facility here to prepare us for a long road of training for EVAs, which is super fun. I did my exam just yesterday on that. And we're doing many more topics as well. Upcoming is, we also did medical training. So I got to learn to do like IVs and catheters and stitches and all this kind of stuff. And we used AR goggles in order to understand the body systems and how they're affected by microgravity and countermeasures. And there's so many more topics. But yeah, next up, we're looking at things like sea survival skills in Northern Germany, winter survival skills, centrifuge training, hyperbaric chamber training. We do language training. We do psychology, and we do material science and fluid science, and we learn about the space station and how to operate the robotic arm. So yeah, having the engineering background I do, I hope continues to set me in as a good basis for doing all these topics, but I certainly love the breadth of it, and that we're forever sentenced to learn, I would say.
Thank you so much. What are you most excited about right now about your role, right? With being an astronaut once the training is finished?
Oh my goodness. I'm excited every day. I'm living the dream, honestly. This is a dream come true. But at the end, ultimately, of course, I'd love to go to space, right? That's the dream for me. And, you know, to be on the space station doing science, particularly Australian science for scientists, hopefully supporting some of their breakthroughs would be incredible. I'd love to do an EVA. You know, can you imagine opening that hatch and stepping out into space in a spacesuit? And I think the dream for many astronauts today would be a lunar mission ultimately. But, you know, for me, if I can help open doors for other Australians that don't have dual passports to have the chance to be an astronaut, that would be something I'd be really proud of. So I hope that I can help to unlock opportunity, first of all, just to be involved in human spaceflight in any way, and longer term, when the time's right, for there to be more opportunities for Australians to do what I'm doing. Would be incredible.
Thank you. So it's really been your dream so far, but has things, now that you're actually here, is anything like you were not expecting it to be? Or do you think, yeah, were your expectations met with all of this?
Actually, my expectations have been matched. I've been asked that question before, and I was surprised in the moment to be like, no, actually, it's just kind of what I expected. I think because in the selection in particular, you study so much what's involved that you get a good sense of it, and ESA puts out good materials and good explanations directly with you and publicly, so you have a sense of it. But yeah, it's perhaps, I'm not sure if it's a surprise, but what I definitely appreciate is the level of camaraderie that we have in the basic training class. You know, we're all in this together. We're not in competition with each other at all. There's no competitive aspect to the training. You're just doing the best that you can. And that's something that I really appreciate.
That's really interesting to say, because I know like a lot of people, sometimes they have this dream and then they end up making it. Sometimes it's not as they expected, but it really seems to have been right as exactly what you wanted in the end. So
I'm sure there'll be lots of surprises on the way, but good surprises, I'm sure. I mean,
good
anything
surprises.
that's a challenge can be fun to overcome together.
So we'll wrap this up with one last question. So for our audience, we might have current Cranfield students, some alumni, some younger students as well who are looking to pursue a career in space. What advice would you give to these young professionals who are just starting their career right now and who might wish to follow some of your steps as well?
I would say you picked a great field. This is an absolute pleasure to work in space. You can have such a diverse career in whatever area that interests you and suits you the most. If you don't get a space job right away, because it can be hard to crack in as a graduate, pick a job in an adjacent field which has transferable skills. Don't wait and do nothing. Like, really just roll up your sleeves and work in an adjacent sector and find your way across, because space is growing. There'll be more opportunities to hop back in mid-career, and you'll have special skills that are unique that you can bring. To work in space, I'd say it's good to network widely. You're blessed, you know, 10 years after I graduated, 13 years, oh my goodness, after I graduated, that there's so much material, like conferences like these that you can attend to get a real sense of how the industry works. Network well and learn from the people around you and their experiences, because you've got to expose yourself to the different parts of space to know what suits you, both your strengths and your interests. So for me, when I did my internship at ESA, I was in thermal engineering, which I really enjoyed. But after a few months, analysis I found got a bit tiresome. I enjoyed it for like 5-6 months, but then I realized, you know, I need a bit more personal interaction in my daily work, not just in the team. And next to me was a concurrent design facility. And I wouldn't have even known day to day what that meant without seeing it. So I think by exposing yourself to more types of space topics, you'll learn more about what you can do, apply everywhere, do what you can. I understand many students at Cranfield are international, so you'll go from this situation where you all have equal opportunity at university to having visa challenges, and go where you can work. And as you progress in your career, you have more mobility. And if you end up back in your home country, see it as an opportunity to contribute your expertise, because it's really wonderful to be able to do that. Be internationally mobile if you can, and believe in yourself. Like, there's so much to be done in the field of space. A lot of it's not solved. And yeah, take the initiative to contribute. Work wherever there's a job that interests you, whether it be a prime, a startup, an agency, hop between them. And yeah, trust that the knowledge you've learned at university has set you in good stead for that. That would be my main advice.
Thank you so much. It's definitely great to see how passionate Cranfield alumni are about space. I think most that I've talked to, they're all so happy it's the area they picked. And I know ultimately it does take some time sometimes to get into the right company, into the right position that you might want, but ultimately it's just continuing to try, continuing to apply, as you said, never to give up, because it's your passion and effort that will carry you through in the end. Well, we've come to the end. Thank you so much, Catherine, for your time. It's really great to have you. I wish you all the best with your astronaut training, and hopefully we'll see you in space someday soon.
Thank you so much. It was a pleasure, and I wish you all a wonderful conference. I'm sure it will be. Thanks for having me.
Thank you. So that wrapped up our interview with Catherine. She was really great. It was such a passion being able to meet and interview a Cranfield alumni who's going to be an astronaut going to go to space. Such an honor to talk to. I wish you, and we wish you all the best, Catherine, with your astronaut training. It's a hard process, but you will make it through.
It's really interesting, yeah, to see, like, to hear firsthand, like, what the entire process is like from start to finish. And yeah, you can really imagine, like, the disappointment when you don't get it the first time, but then you just keep trying, I guess.
That's the biggest takeaway from this. If you're wanting to pursue a career in space, or maybe even become an astronaut yourself, just keep going at it. Just keep trying. Catherine had a lot of hurdles, up and downs, and she's made it in the end. And it could be you as well. Maybe for a lot of our colleagues, sometimes you might not be able to get into your first preferred company right away, but as long as you try, you will make it through. It's just a matter of keep going, persistency, tenacity, and you'll make it. Maybe you'll be amongst the stars one day as well.
And don't forget, if you have any questions for Catherine, you can send them to us and we'll forward them to her and get back to you.
So next up, we will be having a panel discussion after the break, including a lot of members who we'll be introducing later. The panel will focus on air and space politics and laws, so it's quite a different topic for a lot of us who are more accustomed to engineering, but a curious and interesting panel nonetheless. We hope you've been enjoying the conference so far and that you'll continue to join us for the last panel discussion of today, starting at 12:45, so after the 15-minute break. 2:45, yes, after the 15-minute break. See you all then. See ya.
Thank you.
Welcome back, everyone. Thank you for waiting for the last little breakup today. Now we'll be joined for a panel discussion on air and space law. We have quite a few guests coming in today, and they'll be here answering a lot of questions, that have been asked already by you, the audience, today. A lot of interest in the topic of politics and law when it comes to space. Such a new emerging topic. We're joined today by 6 guests. I've talked a bit about them already before. You can see them here on the screen. Our 6 guests that we have in order of left to right. We have Dr. Brad Tabas. He's a lecturer at Ansta Bretagne in France. We also have Julia Speak, a commercial executive at Rolls-Royce. We have Bernd Weiss, a researcher at the University of Luleå in Sweden. We also have joining us 3 members from Clyde & Co., the global law firm. We have Carol Anderson, senior associate. We have Gabriella Mifsud, air and space lawyer. And finally, we have Darcy Downey, consultant, who is working at Clyde & Co. at the branch in the United Arab Emirates. Thank you so much all for joining us today. We are going to just hop right into the first question, which is a easy one, I would say. Could you just introduce yourselves a bit? Tell us a bit about your career so far and what got you here, and are you working on any projects as of right now? Let's start with Dr. Brad Tabas, as you're the first one on the screen on my end.
Okay, so I'm Brad Tabas. So I'm a philosopher, and this means that I'm not, as it were, a specialist in law or politics, but someone who's interested in pretty much everything that has to do with space. I actually am really excited about the subject of the conference today, or of the event, because I'm really interested in sustainability, and I actually came to space working on sustainable development questions, and I stumbled onto Gerard K. O'Neill's High Frontier. And at first, when I started reading that, I was very critical of all the people working on space, because I was coming from working in the sustainable development, which is very Earth-focused. And then I started to learn more about space, and I realized that there was a lot that could be done for sustainability for space, from space. And so now my position is that I a little bit disagree with everyone. I sort of disagree with the space people because I think they don't think enough about the Earth, and the Earth people because they don't think enough about space. And so I'm sort of always in this unhappy middle of trying to get everyone to think about what they're not thinking about, and that's what I mostly do. Okay, so whoever's next.
Thank you so much. Next up, Julia, if you want to introduce yourself.
Hi, good afternoon, everybody. So my name's Julia Speak. I work for Rolls-Royce, and I work in our defence division. So I guess I'm really interested to be part of the panel this afternoon to provide a bit of a contrasting perspective as space travel and commercialisation grows. I guess hopefully I can bring an interesting perspective of what I've learned from working. I've worked for Rolls-Royce for 15 years, mostly in the defence field, and in particular on international collaborative programmes. Currently, I lead a team of 15 commercial people, so we tend to do commercial and contracting activities. And just to put things into real life, one of the projects I work on is the engine, the EJ200, which goes in the Typhoon, and those were the aircraft that flew at the weekend on the Trooping the Colour Fly Past and made the CR in the sky over London, which is a very proud moment when you see your products flying like that. And yeah, my academic background is in law, and in particular in European law. So yeah, really great to be here, and thank you.
Thank you so much, Julia. Bernd, if you want to introduce yourself as well.
Yeah, hello. I'm Bernd Weiss. I'm originally from Germany. I'm doing a PhD now. After 15 years working in a variety of roles, I thought, let's go back to the university and see what's new there. And I stumbled upon sustainability actually like in mostly like a coincidence maybe. We are looking into space debris and how we can reuse materials in space. So really from an engineering point of view, what are the requirements to reutilize and reuse materials? And from this, I found a lot of similarities to plastic pollution while I went to space debris. And from there, it really led over. We grew the project. Now we're looking into sustainable development, sustainable production, and we really grew into how can we reuse more materials, not just in space, what can we learn from space? Because of course, space is very complicated. If you think about reusing a satellite, it's not as easy as taking back some tons of paper or some tons of plastic. So we need to figure out how we can do this process. And of course, we want to see how can we do it in space and then bring it back to Earth and learn from it. That's pretty much what we're working on. And I'm really excited to be here. Thanks for inviting me. Thank you.
Thank you so much for that amazing introduction. Next up, Carol, if you want to introduce yourself as well.
Hello, everyone. I'm Carol Anderson. I'm a senior associate in the aviation and aerospace team at Clyde & Co, along with Gabby and Darcy. And predominantly my background relates to aviation and aerospace rather than space. But I did study space law at the International Institute of Air and Space Law at Leiden University, and have a particular interest in liability issues for commercial space tourism, commercial human space flight participants, and how the current regulatory and legal frameworks will apply to new space as it develops, which I think Darcy will talk about today in more detail. So I'll just pass over to my colleague now. Thank you very much for having me.
Thank you so much for being here as well. Gabriella, if you want to introduce yourself.
Hi, good afternoon, everyone. I'm Gabriella. I'm a lawyer qualified in Malta, and I currently work at Clyde & Co.'s London aviation liability practice. So I predominantly work on the aviation front. But I did also do the same master's as Carol from the Leiden Institute of Air and Space Law, where I graduated in air and space law. I also worked at a satellite company in the UK before joining Clyde & Co. I have a really keen interest in sustainability, so I do a lot of work on the aviation front, but I'm also really interested in the space side. So I've written quite a few papers on that, and really keen as to how law and regulation can facilitate commercialization with a focus on sustainability. So looking forward to today.
Thank you so much, and that's very much what we'll be talking about soon enough. But last but not least, Darcy, if you want to introduce yourself.
Hello, thank you very much for the invitation. And as Carol said, I'm part of a team at Clyde & Co. I was based in the UAE, and now I've actually just moved back to my home country of Canada, and I'll be based out of the Vancouver office. I have a master's degree in air and space law from McGill University in Montreal, and I've worked in aviation and space, and the space aspects have been insurance-based claims, mainly dealing with third-party liability issues for launch failures, and also assisting states who have signed up to the various space treaties and then want to promulgate their internal legislation so that they can comply with the treaties they've signed up to. For the last probably 15 years, I've worked in international arbitrations in extractive industries and on Earth, and that has really got me thinking about sustainability. And more for me, sustainability is actually slightly flipped on this. Is what I'm very much bothered about is actual access to space for example, developing countries. And from my work in international arbitration, which has mainly been for states who have been come into difficulties with companies, large multinationals and things, to lack of a better terms, of taking advantage of their ignorance of their legal position. And I can see the same things now are just going to be literally thrown up there in space. And so that's what's got me a bit more agitated or concerned about sustainability, because for me, access and sustainability do kind of go hand in hand.
Mm-hmm.
And that's it.
Thank you so much. And that was a really important point that you touched on as well, on the accessibility side of space. A lot of when we looked at, for example, when sea exploration started to become a thing, when a lot of the countries started being discovered, a lot of the exploration, a lot of the accessibility and how it was done was through a lot of the limits that were set were by people who already had a lot of much knowledge. So for example, what was it? It was Portugal and Spain.
Oh, the Treaty of Tordesillas.
Yeah, they split the world in half, effectively which countries each one was allowed to go and explore. And Portugal, because they knew Brazil and a lot of those countries existed, they made the line slightly skewed so it would include Brazil because they knew there was a lot of resources there. And that's something we might be able to see happening as well with space for these countries who have a lot more information. So accessibility is very much a very important issue when we come to regulations and a lot of these things for sustainability for space. So we'll start off, I think, Ian, we'll go for the first question.
So yeah, I think we're just going to go straight into the kind of commercialization side of things. So the space environment, as in the commercial environment, is pretty different from what it used to be. It's not just governments that are involved nowadays. Now almost any company can get involved in space if they want to. So, so then this question is, how do you foresee commercialization of space impacting the landscape in terms of regulation in space? And what are the key challenges in kind of establishing frameworks for that kind of regulation? So we'll start off with Brad, if you have something to say about this.
Okay, yeah. I mean, I do have something to say. I'm going to start off by saying that sometimes I don't like to answer questions in the way that they're asked. So I'm not going to.
That's okay. That's okay.
Yeah, sure. And I'll tell you that the sort of answer I'm going to give is I'm going to give an answer more along the lines of not what I think is going to happen, but what I think should happen. Because actually, I think one of the problems often in space, when we talk with people who are interested in space, they're very interested in the future. And so they don't tend to think maybe enough about the past. And they also tend to be very interested in sort of getting to space as being an end in itself and not thinking enough about what are the real points of going to space. And so I think that a couple things that I think should happen with respect to the space economy is that right now with the space economy we have a rush of these new actors in space, and I think that from the viewpoint of sustainability this could be a good thing because a lot of what these actors do are sell services to the Earth, and those services can increase sustainability by optimizing processes on Earth, like most of what the satellite companies are selling have some direct relationship to doing that. But it can also generate a lot of inequality on Earth because only some people live in countries that have access to satellites and other people don't. And so I'm very concerned about this distinction between like people and planet. When you talk about sustainable development, the idea is to have a people, planet, and the economy all fitting together. And I think that one of the things that happens with the new space economy is it can drive apart the interest of the people on the planet and the environment, because we can do things in space that are interesting for the environment, but also can cause inequality. And so I think that a couple of things need to happen. I think one, in terms of the legislation, it would be really important to start not talking about space as a sort of indifferent mass, but start getting really clear about how people use space, and have sort of ask questions. For instance, we talk about these graveyard orbits. If we talk about sustainability, putting stuff in a graveyard orbit, like someone was talking about before, that's a little bit like putting our trash in the river and saying that's sustainable development. So there are problems with how we think about sustainability in terms of space for space. If we talk about questions like these very interesting discussion of putting solar panels in space, it's really great for sustainability, but that's over somebody's house. You'll be able to see that from Earth, and some people will be unhappy with that because maybe they like to look at the stars and they'll be unhappy with it. So those kind of conversations between things in space and Earth have to be brought in. And then the second thing, so this is really a question of having zoning of space based on what we actually do, because the beginning laws, when we created them, if you go back and you look at the original drafters of the laws in space, they really expected people to go live in space. And that's not how we use space now. So we really need laws that are more adapted to that and focusing on how we use it and where, and have that specificity built in with respect to how it affects users on Earth. Another thing that I think has to happen is there has to be redistribution. And I think this is something that is not going to be baked in for the space economy. I think a lot of nations want their citizens to earn money in space. And so I think counterfactually, this is going to be hard to do. But in principle, space belongs to all humankind, right? I mean, that's what the OST talks about. And so it would be great to have redistribution of the wealth that comes from space, because one of the things that's interesting, if we look back historically, in fact, there was a chance to increase the space economy back in the 1960s, but JFK did not want to have privatization of space-based communications at that epoch because he was afraid that people in poor countries wouldn't have access and that the access would only be given to richer countries. And he was afraid those poor countries would then be given access by the Soviet Union, and that would be a catastrophe for democracy, right? And there's something like that in play, but there's no one protecting democracy now. So I think there's a lot of incentive to provide services to richer countries because they're the people that can afford to pay for it. But I think that the real benefit of space-based technologies is that they can provide services to people in areas that right now don't have land equivalents. But I don't think that the social justice that could be generated by that will necessarily be fostered by having privatization of space. So I think that there should be some sort of redistribution to ensure that people's benefits on Earth are equally distributed. That's another thing that I would like to have happen. I don't think it will happen, but I would like it to happen. And then finally, just to sort of close with things that I would like to happen, is that I think that there's a big role for governments in terms of paying attention to things like waste in space and paying attention to things like accountability in space, because private industry does not want to pay for that, and governments really should pay for that because that's what they do on Earth, and they need to have some sort of agreement among different government actors to put in place that sort of governance because it's a big service to allow to have space to develop. And I think I probably hogged up my time, so I'm going to pass the question to whoever else wants to talk now.
Well, yeah, for sure. Like everything you mentioned was really important and really interesting, especially because at least in our MSc, we don't learn about any of that.
Yeah.
Like for us, the goal is to get to space, and what's done there afterwards really isn't talked about. So like someone definitely needs to look at it for sure.
Absolutely.
So then for the next speaker, Gabriella, I think your work is really relevant to this question. So if you have something to say.
Yeah, me and both my colleagues probably have a lot to say on this. I know Darcy definitely does. I think, well, there is at an international level, what's really lacking is that there isn't sort of a global organization that can take everything and sort of funnel that through, right? So for example, in aviation, we've got ICAO, which has been really good at establishing rules and regulations over the years, where at the space level, we've got the committees at UN COPOS, the United Nations, but then we haven't got sort of an organization, an international organization that funnels all the voices of all the states and sort of channels that into a single position. At this stage, I think we're still quite early in the sense that obviously sort of the space race is being dominated by the countries that can afford to spend all this money basically and doing these things. And unfortunately, it does get very political in terms of what happens where and who has the resources to go up there and do certain things. But I think the real sort of regulatory issue is really sort of allowing innovation to thrive and to proliferate, but also ensuring that there's safety and that we get there slowly instead of trying to jump the gun. I think that's the main issue really. I think Darcy would also probably mention the Space Benefits Declaration, but I'll leave that to you to go ahead and give your input on that.
Yeah, for sure. Thank you very much. If anyone else wants to come in on that.
Yeah, if you want to comment a bit on it as well, Darcy, as seemed to be...
Okay, yes.
Yeah.
I agree with Dr. Tobes in that, we've been thinking about this slightly askew. The legal framework is already there. Space is one of the few places we codified before we got there. So in comparison with, say, what's happening with AI at the moment, where everyone's jumping up and down and saying, oh my goodness, now look what's happening. And now they're looking at it. So the fundamental foundation is there. The space treaties do set this out. It is just whether there's a willingness to hold private industry at the moment's feet to the fire. And I think that we'll never we're never going to agree another space treaty that deals with modern times. I know I'm sounding very pessimistic, but you know, these were all agreed in the 60s, and that was I guess a golden age for international cooperation in treaties. And now we can all argue for about the next 3 weeks about how vague the treaties are about different things, but there is a fundamental framework there. This is not the arguments that we use to bring in imperialism and all of that type of stuff. It's not terra nullius. This is not a place that has no laws, and therefore it's a land grab. The whole reason for the treaties was to try to avoid just what we're seeing now, which is first mover private companies going behind the treaties to say to nation states, we're going to invest in this, aren't we good? And you need to recognize our private rights in space, to the detriment of everybody else. The East India Company and all of that imperialism didn't work the first time around. So why are we thinking it's going to work this time? So that's a bit of a rant, but then getting back from that, my fundamental point is this, is that the treaties, if we care to look at them, do set out a very good framework, and indeed for sustainability, because they, in particular the Outer Space Treaty of 1967, says other international laws are applicable, not just, so laws on land dealing with environment and safety and all those things are naturally and legally applicable. Now, I know I'm sitting here, you know, with ivory tower lawyer, but like I say, this is not an issue where we have to reinvent the wheel. The wheel might be a little bit flat, but it's certainly there, and that is my view. And like Gabby said, there are different organizations that have looked at, and we can talk about that some more, but you know, the space benefits. But I feel, and I know that it sounds slightly unreal. It's not meant to sound unrealistic, but these features that we already have can and should be followed, and it's not just a matter of saying we would like them to be. In fact, hundreds of nations have signed up to these treaties. They've been in place for over 50 years. So that is my position on that. And like Gabby says, we probably need to push our various regulators and governments to look back at this, and that's probably via COPUS, which people say is a kind of, you know, very slow moving body, but it is formulated under the treaties. And that's the end of my rant.
Thank you so much, Darcy.
We're actually going to touch on some of what you mentioned later.
Yeah.
About like the different interests in space nowadays. So that'll be really interesting to expand more on.
So it actually touches on really well on our next question, Darcy, from a lot of what you mentioned. So as space is becoming more and more accessible, especially with the privatization and commercialization, how can we ensure that these sustainable practices are incorporated in these organizations, into these operations as well? And what role can regulatory bodies really play in promoting environmental responsibility in space? Do you want to tackle that, Bernd?
Certainly. Great question. And I really like this conversation about space law and the prior question. But so for me, from a point of research, is really the question, what comes first? Is it innovation or is it the regulation? What happens in the beginning, and who is influencing what? Is it innovation the driver for regulations, or are regulations the driver or barriers, or even a lack of regulation could be a driver for innovation in that sense? But if we want to really look forward into the future, that's what I believe even strongly, and what I'm advocating for is we need to come up with regulations that are supporting innovation, kind of like in the automobile industry we had with like catalysts in Europe with low emissions standards and so forth. We need to come up with really good regulation that is accepted on a global level, that it's like maybe even drafted on a global level together, and that's kind of like also, of course, enforceable, because at the moment, if somebody has a satellite in space that it's defunct, it's not really so hard enforceable because we don't have technology yet to capture satellites to pick up the garbage behind us. So it's of course a little complicated there, but I believe really working on these regulations to support innovation in a sustainable way. And then of course we need to focus, and that's for me the main goal. Reuse should be our prime directive, if we want to say so. Reuse of materials, reuse of stuff in space that we put up there has to be first reused and not just disintegrated into space. And if it comes then to the place, regulations should force companies, and gently maybe even forcing companies, to implement reusability. We have in Europe, and Darcy said it perfectly, we also have these regulations that are already existing on Earth, which we could apply. So what happens with the right to repair, what the European Commission is trying to work on? Will that mean that if I order a satellite somewhere, a spacecraft, do I have the right to repair it somewhere in space? What are the satellite operators then helping me to do these things? So there are a lot of questions we need to figure out over time, but I believe in these 2 points, like regulations need to support it, they need to force companies to implement reusability, and then from there we can see where we can go.
Thank you so much for that. Darcy, do you know if anyone in your group would want to tackle as well this question? Maybe Carol, if you want to give some thoughts as well on this matter, or any of you three, it doesn't matter.
I just wanted to make the point that regardless of the role of ICAO, UN COPUS, and all the various committees, the model in practice seems to be following the aviation industry. The FAA has had a significant role so far in relation to American exploits. And in 2021, the UK CAA was named as the UK space regulator because the infrastructure is already there, basically, in terms of regulatory expertise. How this will play out is anyone's guess in practice as new space becomes more developed and more active. But I just wanted to make that point. It's interesting that this was one of the things I talked about in my thesis. We were looking at how it would be looked at from a regulatory perspective, and because of the advanced nature of aviation regulatory and aerospace regulatory institutions, almost 100 years, let's say, of experience, then it makes sense that they would take over this initial early to mid stage of operations in space, I would say. Do you agree, Darcy?
Yes, we can. It doesn't seem to, at first when we heard the FAA and the CAA, it seemed a bit counterintuitive, but like you say, especially in respect of space, public access to space, I'm not certain it's necessarily the right place for private commercialization if you're just looking at exploitation of resources and things. But it is what we is. But getting back to the UN, and I know people probably like to bash the UN, but there is 2021 they did publish, and the panel probably knows this, their guidelines on long-term sustainability for space activities, and that's quite a detailed paper that sets out the different levels of the framework for space activities, safety, cooperation, and scientific research. Now, it is a UN document, so it is diplomatic in nature. It covers a lot of things, but again, like I've keep saying, is we do have a framework, quite comprehensive framework for quite a lot of these things. And now there are different organizations like the UN, and there's something called the Lunar Policy Handbook that came out in 2023 about specifically looking at the moon and sustainability, and again harking back to the treaty. So some of these things, people are thinking about it and trying to give frameworks for today, very much based on the historical international laws that are already in place. So again, some wheels don't have to be reinvented, they just might have to be inflated a bit more.
If I can add to that as well, I think what we really need is for sort of governments to take a look at, what's happened in other industries, what we've done in other industries, and how that can be translated into space. I think a lot of it is really just sitting down and thinking how we can creatively overcome these issues. And there is a lot happening. So, for example, a lot of companies are investing in on-orbit servicing. So, governments could mandate that new companies that come in and look towards applying for a space activities license would need to have contracts in place to do on-orbit servicing for their satellites. And that could be done on a point system, so that if you have that in place for the future, then your license will be more likely to be granted, because you're contributing towards the sustainability of your operations. There's also something called the Lloyd's Kite Mark for sustainability. Which is really good from an insurance perspective, where if you can show that your operations are likely to be sustainable and are more sustainable, then your insurance premium may be lower. And all these sort of little bits and pieces that can not only help the business, but also help the state and space at large, and ensuring that it is, still safe to use for other entrants and still sustainable for future generations to come.
Can I add something to this?
Real quick though. Quick.
Yeah. So one thing that I think, so I agree with everything the lawyers are saying, but I do think that there are some questions that are very specific to space that maybe haven't been addressed very much, and there are questions that have been addressed elsewhere too, and specifically questions associated with data and rights to our data. A lot of people are interested with our data on the internet, but most of what we're doing in space is gathering data on people. And when it was states that are gathering that, we can say we gave consent by voting for the politicians that represent us. And when the states agreed to have the Outer Space Treaty, Russia and the United States, this was both consenting to be able to survey each other's territory, basically. I mean, that's why they signed that treaty. But we didn't sign anything with private companies to survey us from space and to do surveillance on us from space and to sell us back that data. And so I do think there are questions of rights that might be associated with that could be raised in the future that are somewhat similar to the rights that people are concerned about in terms of internet privacy. And I think that's something that hasn't been addressed very much at all, but it could be a concern.
Thank you so much. That was something I hadn't even considered, that last topic. Thank you all, effectively you 5, for pitching into that answer. Kian, do you want to go to the next one as well?
Sure. So actually, Gabriella kind of touched on this in the last question as well. So with all the conflicting, well, I wouldn't say conflicting, but definitely differing interests with all the different players in space nowadays, we need some kind of way to encourage the different bodies to work together. So what strategies do we have to encourage collaboration between the governments and the companies and the international organizations in space? And how can we ensure kind of transparency when it comes to establishing frameworks? And we'll start with Julia on this one.
Okay, so I guess I've been part of a number of international collaborations at sort of within industry, and I guess one thing I would say on this is that in order to be successful, you need to have that alignment that's coming all the way down from the governmental level. So a lot of the collaborative projects that we have in aerospace and defence, they all start up at the either with a government-to-government agreement or a treaty, and then that will flow down through an airframer cooperation, and then down to the all the subsystems of the aircraft. And that's really, really powerful, because that means you have this collaboration that it is taking place all the way up and down the supply chain in pursuit of a common goal. And it's definitely true that you can achieve so much more when you've got that shared risk and shared reward. You can participate, industry players can participate in projects that would just be out of reach for one company on its own. And I'm sure that's as true of the space industry as it is of aerospace and defence. And I guess just in terms of how to make cooperation work, especially on an international level, I guess there's a lot in there around regulation and having a good legal and contractual framework, and that's a large part of what we work on. But I would say there's a large human element as well, and understanding different cultures, how different cultures can work together and build up trust. Especially when we're dealing in more sort of testing the boundaries of technology and innovation. There was a lot in how we work together and establishing common ways of working, shared goals, shared principles. So yeah, that's my insight on that. Thank you. It's a great question.
Thanks. Yeah. And again, that's the kind of thing that you don't really learn from a college course. When you're as you said, on the frontiers, there needs to be a lot of working together in that. So does anyone else want to come in on that question?
I think only one point just to accentuate that question is that we've all known how long the International Space Station has been up. I mean, 20 odd years or something now. And just like Julia says, is that we've got all this politics swirling around, different countries falling out with each other, a lot of whom are parties to the agreement for the space station. And in the background, they're all quietly getting on. So it's quite interesting on a scientific level, and sometimes on a scientific stroke commercial level, the politics don't necessarily interfere with collaboration, which I think is heartening.
Mm-hmm. Yeah, it's very interesting to consider that, with the different nationalities on the ISS for sure.
I mean, even with space as well, to even get a satellite launched into space, you have so many countries who are liable for all the launching states. So it can get a bit convoluted at times, much more than certain sea operations or sometimes air operations. So it can be a bit convoluted. It is, yeah.
I just wanted to mention the Hague International Space Resources Governance Working Group, which has done quite a lot of legwork in this area of creating a kind of public-private dialogue on the building blocks for the development of an international framework on space resource activities. They produced their work in November 2019, and it's available on the Leiden Institute of Aerospace Law's website if anyone's interested.
Yeah, if I can just add something small at the end. Sorry.
Go ahead.
But just, for example, we're us three, we're lawyers, right? So we don't fully have the knowledge of how the technical side of things work. And I think when it comes to law and regulation, it is so incredibly important for there to be sort of a middle ground between where, the lawyers can grasp at least the basic fundamentals of how space works, how, satellites work, shuttles, everything. Because if you need to regulate something, and if you want to regulate something, you should have a basic understanding of how it works. Otherwise, that regulation will not address the concerns that there are, and will not do anything. So that's why, conferences like these, for example, are so important to bridge that gap in the dialogue. There are lots of organizations, thankfully, right now, such as the one, Carol mentioned, and there's also the Secure World Foundation, there's the Space Generation Advisory Council, which are doing a lot of work to bridge that gap in the dialogue, which is so important.
Can I add to that just very quickly?
Sure.
Yeah, I totally agree with what she said, but I think actually, and it would not make things easier, but I think that public education is really critical in terms of space and governance, because I think what your average person understands about space is people going to the moon, and they really don't understand how the space economy works. They really don't understand what it is. They might understand space tourism and see that as something that happens, but that's not what most of the space economy is. And I think that really having some sort of public outreach where people understand what people actually do in space and what it contributes, for instance, to sustainable development, I think is really necessary because people don't understand that.
Thank you so much. And you touched on a keyword, which I know we're going to be talking about right after, space tourism. So it's becoming a reality. A lot of people are actually starting to fly up big balloons, sometimes rockets as well. You had through the Blue Origin, you had some space tourism flights already being going ahead. So with space tourism, what measures should be in place to ensure the safety of sustainability of such endeavors? And can regulators really strike a balance between promoting this innovation, engagement, and a lot of these experiences with safeguarding public interest in the commercial space tourism industry? Do you want to start off that question, Bernd?
Yes, of course. I'm not really into space tourism, of course. I'm looking more into innovation and how we can get there. And for me, space tourism is pretty much, I'm taking the example what Darcy said. We have a lot of with regular flight and aviation laws. They're also like in charge of security of people. And if you probably followed the news recently in Florida, they introduced a law about the liability of spacecraft launchers and operators and companies, that they're not liable for injuries that happens during the space flight, which I believe is a very important step forward, because if you go in a plane, you don't expect the company to be liable if you have an accident or something in there. While of course, if you want them to be able to have 100% certainty that the tools and the flight and the plane is okay, that the technology and everything else, the mechanics in a plane is working. So negligence is a big topic about this. Of course, you want them to be able to sue them when there's negligence. But in grand total, we need to look into space tourism, in my perspective, as something that it's getting more common, like getting something normal. In 15, 20 years, it would be just something what people do. They just fly up and go on a trip to moon and maybe even Mars in 30, 40 years. And I really think that looking at these things, what regulators can learn from the aviation industry, how do they work with aviation, with insurability of planes, like in spacecraft, what can we do there? And how do we support safeguarding space travel? That's probably the biggest question in my perspective. But again, I'm just like on the sidelines looking at it. And what can we learn from aviation to make spacecraft more reliable, more reusable, and of course then safer on the long term.
Thank you so much. Julia, do you have any comment as well on this question on space tourism?
Yeah, I think Bert makes a really interesting point about what we can learn from the aviation industry, and I guess my reflection on this would be, you think about how many millions of people get on a plane each year, and they do that without really thinking about, there's a regulator and there's this legal framework. They just get on a plane and enjoy their trip and enjoy their holiday. And it's kind of become something that level of trust is built up so that people don't think about it. And I guess, looking at the space industry, I guess that's where we would look to try and get to. And I guess to do that, you need to have that, although it's not very visible to the general public, you do need that really rigorous regulatory framework that sits in the background.
Absolutely.
Can I jump in?
Yeah, please.
Can I jump in on it? So,
please, absolutely.
So I just want to go back to where we are today. And I've got a fantastic quote from the US Congress in 2004. And this is relevant even today. What basically says that the new industry of space is an adventure and not that on the same level as airline passengers. And they say this industry is at a stage when it is the preserve of visionaries and daredevils and adventurers. These are people who will fly at their own risk to try out new technologies. These are people who do not expect and should not expect to be protected by the government. Now, that is the U.S. position at the moment, and it's going to be like that, I think, until 2024, and it should be revisited. So the long and the short of it is, you as a passenger can go as a public access to space on a U.S. vessel, but all that you need to be told by the operator that the vessel is not fit for your own safety. The regulations only extend so far as to ensure that it is as safe as possible to prevent third-party damage on the ground, because obviously they don't want these things going up and damaging innocent third parties. And there's a whole insurance structure behind this. And something more interesting, you have to give what's called, the operator must give the passenger informed consent. So the passenger must give back to the operator informed consent. and it's very detailed about, and obviously this is incredibly fertile ground for lawyers, is what is informed consent in circumstances like Gabriella said, where, well, we know the thing goes up and there's a lot of fuel and then it does, but you know the physics, and Julie and all that, we'll be talking about this. So what is informed consent in such technologically advanced circumstances? And so far there hasn't been any huge losses. And the other thing is the way the insurance works and the way it works in the space industry is everybody gives each other what are called cross waivers of liability. So no one sues the other, and then that means that you insure for your damage, but you're prevented from pursuing the next person. And that is based on notions of trying to develop a nascent industry. But it is agreed, I fully agree, that aviation has been built, the rules of aviation under the Chicago Convention and all the other Warsaw Convention suite of treaties has been built on a lot of spilt blood. And we are now at a position in aviation, like Julia said, where we just fly, and you know, when the flight's delayed, we get a bit of money, and if the worst happens, it is actually relatively straightforward for claims to be made in aviation. And my query is do tourists really need to be going to space? Which comes back to probably the very first point, which is what Dr. Tobas said was, you know, I think we need to examine that point, which is not probably what you want to hear. But just because we can doesn't mean we should. And I do think that that is probably why the US has taken this position. But the fertile ground on the cross waivers of liability, and I'll just finish with this one point, is what I call the widows and orphans issue, where, and this is being very sexist, but the husband spends the family's last $5 million to get to space. It all goes terribly wrong. He signed a waiver so that he's not going to sue anyone. Widow and 6 orphans show up all in black with veils in the courtroom in America somewhere. And you can bet they will get more money out of that manufacturer or whomever or everybody. So, and that's just a very, I don't mean to sound pessimistic. And it's quite timely when you look at this submersible, the Titanic submersible that's gone missing. You know, space is not a safe place. And I've written a few papers on space safety, and I've always compared it to submarines. You know, it's not a place where you want things to go wrong. And so it's an incredibly dangerous environment. And I think we need to think long and hard about whether and I don't mean to sound that it's disparaging, but does the average person really need to go to space? And or does even the above average person need, or does anybody need to go? You know, I think there should be a scientific reason, education reasons, but not just for a jolly. And I'm sure I'll live to regret those words, but that is a position, a personal position, not that of Clyde & Co.
Thank you so much.
But for sure,
I'd like to follow up on that too.
Not too much time, though.
Is there? No. Okay.
No, we have run out of a bit of time. What was?
No, I was just saying, like, yeah, it is important to ask these questions, even if it's not ones that we always like the answer to. But for sure, like, there's all sorts of issues there that need to be considered. So thank you.
Thank you so much, Darcy, for that good closure as well of that argument. Strong point. We've come to the end. That was our last question, the one that we had time for. I know there was some questions coming in through the audience who are very keen on speaking to you to you six. I know you've touched on a lot of topics that have been asked. If they have any further questions, you can send it to us directly and we'll forward to the guests, or you can find them on LinkedIn respectively as well and send them any questions that you might have. I know Chad was quite active during this time, so you might get some questions coming through your way. I just wanted to thank you six for being here. It was a great honor to hear you speak on this topic. Really, really important, really, really enlightening for someone, a lot of us being in engineering, hearing about all this politics, regulations, and law, which is just as important
Well,
in
they
the
tell
space
us
sector.
number 1 is politics,
Yeah.
number 2 is economics, and number 3 is engineering.
Exactly.
So for sure
Exactly.
the politics has to come in somewhere. So thanks, guys.
So thank you so much
you.
for everything. We'll be doing just a little closure now. So we've come to the end of the conference. We want to thank everyone who tuned in to watch the conference. A big thank you. It must have been hard sitting through all this time. So a bit uncomfortable for us as well, sitting here through the whole day. But it was great. We just wanted to thank the studio team as well who helped us organize this conference. They were a pleasure to work with. They did so much support, so much help for us. And as I've said already, and I've said throughout the day, if you have any questions, if you want to, feel free to send it through us to LinkedIn or through our email at cranSEDS@cranfield.ac.uk. That is our email, or on Instagram as well at CranSEDS. We will be posting much more of our updates regarding our projects, our conferences, and much more to come. So if you're interested in what we've done and you want to see more, make sure you tune in to our feed next time. We'll be posting updates to come.
And once again, there were a lot of different topics at the conference today. And they all touched on really interesting points. So again, if you want to know more about any of our speakers, just send us any questions you have and we can forward them. So yeah, it's been a really interesting day. So thanks very much.
It's been really great. I hope you've all enjoyed the stream so far. We won't be doing anything like this probably this year again. Maybe next year we come back and we'll have some of these guests in completely new positions. Maybe Catherine is already in space. She'll be able to join us, tune in from space. That would be really great. And it was a pleasure to be here with you all. I say my farewell here now today. Thank you so much for having us. My name is Sarah.
My name's Kian.
And
thanks so much, guys.
Thanks so much.